Very good evening to all those in India, and good morning to all those who are joining from Canada. And probably, if you're joining from anywhere in between India and Canada, good afternoon uh, or good late morning. I welcome you to this workshop on advances in 3D printing. I will hand over now to our moderator for the first half. It'll be Professor Wahid Sadiqian from Carleton University in Canada. So, Wahid, please take over.
Thank you, Manu. Hello, everyone, and welcome to this half-a-day symposium on 3D printed concrete. My name is Wahid Sadiqian. I'm an associate professor at the Department of Civil Engineering at Carleton University, and I have the pleasure to be the moderator for the first half of the session. So this symposium is sponsored by IC Impacts, India, Canada Center of Excellence, as well as the Ministry of Science and Technology of India. We have planned 8 presentations on various topics of 3D printed concrete. And I'm sure that all presentations will be very exciting. And hopefully it will provide us with some opportunity to learn about the progress on various aspects of 3D printed concrete in both countries. So each presentation will be 20 minutes. I will kindly ask all of our presenters to keep track of the time. We have a very tight schedule. I will give a 2-minute warning at the end, before the end of each presentation, so the presenters know about the time. At the end of each presentation, we'll have a 5-minute question and answer period. I would like to ask all of our participants to please stay muted throughout the session. If you have any questions, you can write it in the chat box. We will monitor the chat box and ask your questions from the presenter at the end of the presentation, each presentation. So please stay muted so we can have a smooth transition between the presentations and effectively use the time. I don't want to spend too much time on introductory remarks, so without further ado, I would like to invite our first presenter, Professor Manu Santanam, to please share his screen. I'm going to stop sharing. Professor Santanam is a professor in the Department of Civil Engineering at the University of IIT Madras, and today he's going to talk about a systematic approach towards mixture proportioning of 3D printed concrete. So the floor is yours, Manu.
Thank you, Wahid. And once again, greetings to everybody who's on this workshop. I'm Manu Santhanam, professor at IIT Madras, and I'm going to talk about a systematic approach towards mixture proportioning of 3D printed concrete. There's a lot of inputs coming in from present and past PhD students, as well as my colleague, Professor Ravinder Gettu. Now, just to put things in context, we understand that 3D printed concrete is a very special material, and it needs to exhibit various special parameters in order to be able to get printed properly and for the structure to be stable once it is printed. I'm sorry, is my screen visible? I just didn't check on that first.
Yes, we can see your screen very well.
Thank you. Yeah, so there are some parameters that are critical for concrete to be printed successfully. This includes pumpability, which involves, of course, pushing the concrete through the delivery pipe to the point where it's driven out of the nozzle. We have the extrudability, which talks about how well the concrete can keep its shape once it comes out of the nozzle. Buildability refers to the property of 3D printed concrete, which enables concrete to get printed in layers without significant deformation. And finally, it also needs to evolve its mechanical properties over time so that the structure that is printed remains stable. All this has to be done, obviously, with the required level of geometric tolerance that is required for construction of the building. Now, because of all of these characteristics to be met together at once, the mixed design for 3D printing can be quite challenging. One of the aspects that is common to most 3D printed designs is high cementitious content, because without higher cementitious content, all of these characteristics cannot be controlled together. There is a carefully selected and graded aggregate that is typically used in 3D printed materials. You can't really use the freedom, or you can't have the freedom to choose aggregate like you do for normal concrete. It has to be a little bit more stringent in terms of your particle size gradations and everything. The other problem that appears because of all of these issues is that the resultant mixtures are poor with respect to economy and carbon intensiveness, because high cement content obviously means your carbon footprint is very high. And the difficulty in using normal aggregate and making sure that you're only using specialized aggregate, which is well graded and satisfies all your criteria, that makes it quite difficult to make sustainable. Okay, in today's world, sustainable refers to things which are economical at the same time are low carbon footprint, but that is not happening with most 3D printed systems that we know today. So mix selection is very tough when we choose alternative options for cement and aggregate, which are required obviously to reduce the carbon footprint. And there are multitude of choices available in terms of what you can use as cement replacement material. And most of these are well known to us. But at the same time, how does the mix design get altered when we start using these alternative materials? At the same time, when do you change your aggregate? How do you control your characteristics of the concrete to ensure that you can get printability despite changing the aggregate type? And what are the critical parameters that will affect the overall printability? So if you look at the process itself, the desired properties can vary depending upon what stage you are at in the 3D printing process. So I'll just get the pointer on so that it's a little bit clearer. So of course, the pumped concrete is going through the hose to the final delivery system, which has the nozzle. So at the point where it's getting pumped, it needs to have a moderate yield stress and low plastic viscosity so that it can easily move through the pipe. Once it is at the nozzle, it needs to be extruded properly. And here, again, we require a moderate yield stress, because if it has a very low yield stress, it will simply not be able to keep its shape. And it needs to have a low plastic viscosity to be able to flow out of the nozzle without much difficulty. But once it is in place, once it is printed as a filament, and then you have additional filaments being printed on top, it needs to have a sudden increase in its yield stress and also plastic viscosity. And what essentially we want to ensure that the concrete mixture that we are designing has the right level of thixotropy to achieve these kinds of varying properties. So all of the aspects about mix selection are towards addressing the rheological characteristics which make all of these different combinations of performances possible. Now, while we can resort to rheometers for obtaining the right level of performance, there are alternative test methods that we can also use for assessment in case there is difficulty in actually getting access to the expensive rheometers. So you can use a vane shear test, which we are quite familiar with in civil engineering. It's used quite extensively for geotechnical investigations. You can use a flow table test for understanding workability and tension, penetration test for setting time, forced bleed test, which is basically derived from what we typically do with binding mortars in masonry for understanding the resistance to phase separation. And you can also do some compressive rheology measurements like this squeeze flow test to understand the link between rheological and very early age mechanical characteristics. And finally, of course, we also want to determine the early and later age compressive strength in order to be able to assess the evolution of the mechanical characteristics. So let me go through these tests and show you how they can be used towards designing concrete in a systematic fashion for 3D printing. So first is this vane shear test. It's a very well-known configuration to most of us in civil engineering. We use it a lot in geotechnical investigations. You have, of course, a vane inside a larger cylindrical cup. And your idea is to simply rotate the vane at a constant speed. When you do that, the shear stress basically builds up, reaches a maximum, and then stabilizes at a lower value. The initial shear stress or yield stress that needs to be overcome for initiating this flow in the concrete is taken as the static yield stress. So that measurement is actually the measurement of the static yield stress. Of course, the same can be done with the rheometer, but again, in the absence of a rheometer, which is obviously not there in most of the labs, vane shear tests can be quite useful. If you look at the results that we have with different binders, there are various different concretes that have been made with fly ash, slag, limestone, calcine, clay cement, and so on. So you can see these are the mixed constituents in kilograms per cubic meter. You have 660 kilograms of cement and 165 kilograms of fly ash in this uh, uh, your sorry, uh, in your reference mix, and then you have the slag mixes, which have equal quantities of slag and ordinary Portland cement, and you have the LC2 mix, which is basically cement replaced partially with a mixture of limestone and calcined clay. What you see here essentially looks at the flow table spread versus the time. As expected, obviously, the flow table spread goes down with respect to time. But what you can clearly see is that up to a certain period of time, let's say between 30 and 40 minutes, you are still able to maintain a flow of about 80 to 85%, which may be significantly high enough for you to be able to do the right level of pumpability and extrudability. But once you measure the yield stress with the vane, you can see that with respect to time, there is a significant growth in the yield stress, which shows that there's some structuration that is happening in your system. So that's what we're capturing with the measurement of yield stress from the point of mixing at different time intervals. That's what we're trying to look at, is how the yield stress actually changes with respect to time. So why is this important? Because once we print the first layer and we put the second layer on top of it, the yield stress needs to be high enough so that deformation of the first layer does not happen because of the weight of the second layer. So we need to ensure that the mix we design has this structural buildup which is suitable for ensuring buildability is achieved in your concrete mixture. Now, what is interesting to note is, irrespective of the binder time, the initial yield stress seems to be in a narrow range, and the flow table spread is also fairly in a narrow range for the printing system that was chosen for this particular study. Again, this shows that we can define very clearly the initial workability of the concrete based on the type of printing system that is available, and it works for various different types of binders. And what we have also seen is when you change the aggregate type without changing too much the particle gradation, you still don't see any major changes in these figures. One thing you can also do is add to it with a gravity-driven slug test, which is getting very popular now. It talks about the slugs that are formed when you actually start extruding the material out of the nozzle. You allow it to drop based on its self-weight, and you can use that to calculate what will be the yield stress at the point of the mixture coming out of the nozzle. So you can somewhat equate that to the dynamic yield stress. That is, once the material is in flow, what is the extent of yield stress it exhibits? And it sort of very well correlates with the actual yield stress measurements that you get from a rheometer. The desorptivity approach talks about looking at pressurizing a mortar mixture, which has been freshly mixed using an inert gas, and collecting the bleed water that comes out of the other end, right? So what we want to ensure is when we are trying to push this material through the pipe and through the nozzle, there should not be any phase separation between the liquid and the solid ingredients. We want the material to come out in a consistent form out of the nozzle. So this is a very simple test to set up, and one can define a simple coefficient which looks at the amount of bleed water plotted with respect to the square root of time. The slope of this can be taken as a desorptivity coefficient. And what we've done is use this as a measure to arrive at an index, right? Because of the total time that we actually expect this concrete to be in the pipe, we are using that to arrive at a measure called desorptivity index, and arriving at a parameter which we have termed as IC norm. This is actually there in one of the papers published by my co-author Rahul, who will also be a speaker in this symposium. So using this, we were able to see that once we are able to define this IC norm value, and if it's 0.03 or lesser, we see that the concrete is actually extrudable. It fails the extrudability test if the IC norm value crosses the 0.03. The details are there in the paper, so I'll not really spend too much time on this. But yeah, all this shows is you can actually employ a very simple approach to really investigate whether your mixture is capable of withstanding the pressure that it takes in the pipe before it gets extruded. And what we have seen is we can also extend this to lightweight expanded clay aggregates, which were used partially as a replacement of the sand. Again, we were able to use lightweight aggregates also in this test, and we saw that we could actually set up a similar kind of a characteristic norm for concrete with lightweight aggregate. The space flow test is actually a compressive rheology experiment in which you maintain a certain height of the concrete placed between two platens, and you move the platen at a very set velocity. Here we are keeping the velocity constant of at 0.5 millimeter per second. And what you'll end up seeing is actually a plastic flow deformation of the paste that is inside. Now, what we want to choose for good buildability is a concrete that exhibits less plastic flow and sort of enters somewhat of a strain hardening behavior. I'll show you what really happens in the system. So you have, of course, an elastic zone of deformation, followed by a plastic flow zone, and then you have somewhat of a strain hardening. Now, this is not the classical strain hardening that we know in solids, but essentially what is happening is the particles are getting close enough so they can actually bridge and then take care of the stresses that are being felt by the material as it is getting squeezed between the plates. So what we need to do in order to select a material that is buildable is to reduce the zone that is here. That is the plastic flow zone needs to be reduced so that when you actually load this material, it goes directly from the initial elastic zone to the strain hardening, or rather strain hardening equivalent in a fresh state. So we found that this was quite a useful way to actually characterize concretes that are more buildable than the others. So here you can see very clearly this experiment being done in a strain control experiment. So you have a constant velocity of the platen movement, and what you're seeing is this mix is actually cracking before it deforms too much plastically. So essentially what we are trying to do is shift the behavior from a plastic flow more towards this sort of a semi-solid type behavior with the addition of an accelerator to the reference mix that is with the fly ash. Now, one advantage of using concrete mixtures that have calcined clay is that you can actually get this buildability without using accelerator. So that's what we saw compared to a reference mix. You see that the mix with limestone calcined clay cement is able to actually get much better buildability, and which can be investigated quite easily with the help of the space flow test. Again, using the same kind of an approach, we were also able to demonstrate that when you use binders which are difficult with respect to rheology in normal concretes, they can actually extend the range of performance with 3D printed systems by increasing the amount of aggregate that you can use in the system. So you can see that the conventional concrete mixtures that we see in 3D printing have a aggregate to binder ratio typically at 1.5. But with concrete mixtures that were made with LC3, we could actually push this up to 3, aggregate to binder ratio of 3, which is similar to a regular mortar or concrete. And we still got excellent buildability and printability performance with this kind of a concrete mixture. Of course, you can see that the surface texture here is probably not as smooth as here, but still, in terms of buildability, you can see that we are able to print these 1 meter tall cylinders without really any difficulty, even with the aggregate content is such a high level, 3:1 ratio between aggregate and binder. Very often we come across possibilities of utilization of waste in concrete. One of the waste, obviously, is what you get from crushing old concrete. These days, a lot of recycled concrete aggregate is being used in new concrete production. But when you actually do the crushing of the recycled aggregate, a lot of the fine paste comes out as filler, which is less than 300 micron in size. You can see this dust flying out when you do the crushing. A lot of this dust consists of very high quality cement paste particles, which can, and very fine silica particles, which can actually be a very good extender for 3D printed concrete combinations. So again, if you have a good crushing process and a good separation process of the adherent mortar from the coarse aggregate, these fines can actually make up nearly 20 to 30% of the volume of the concrete waste. So what do we do with this waste? Of course, they are not really good as aggregate, but they have a really good future in terms of using as an alternative cementitious material. So once again, we adopted a similar approach as what I've showed you with the other kinds of tests that I described to select the right kind of material characteristics. We used the concrete mix, which had the limestone calcined clay combination as a replacement of cement. And we looked at introducing the waste concrete fines also as one of the binders in the system. So what we saw essentially was that in the squeeze flow test, we could actually make out that many of these systems were not reducing the buildability of the concrete at all. In fact, the waste concrete fines, because of its fineness and because of its water retentivity characteristics, was able to make the mixes a little bit more buildable as compared to your typical LC2 mixes. Again, in terms of strength, these are all the printing trials that we did with the waste concrete fines, which actually helped us get good printability even with 30 to 50% replacement of the binder with this waste concrete fines. Now, this is actually showing you the buildability assessment with 30% waste concrete fines replacement. either the cement in the LC2 mix getting replaced or the LC2 getting replaced directly 30%, keeping the cement constant. So what you see is there is distinctly a methodology that has been created with which we can evaluate these alternative binder systems to obtain suitable performance with respect to printability by adopting this systematic approach to the mix design. So all I've said is utilize these test methods, which are fairly easy to use, to set or define very clearly the parameters that are required for producing 3D printability. There's the work of one of my master students, Mr. Aniket Patel, has actually, I'm hoping it will get published soon, so I'll be able to share a more detailed part of this work that I've just presented in this paper. In terms of mechanical properties, again, you're seeing that the use of waste concrete fines does not really reduce the strength significantly as compared to your reference mix, which is here, which is the mix with the cement and the LC2 combination. There's a slight decrease at 3 days, but at 28 days, you really don't see much of a change, except for the one where you have the 100% replacement of LC2 with waste concrete fines. Partial replacements seem to work much better than the reference mix in this case. Right, so what I wanted to essentially capture in this presentation, because very often the needs for what the 3D printed concrete is being applied for are quite different. And based on the needs, we can actually fine-tune the design mixes to really achieve the combination of characteristics that define extrudability and buildability. Now, the issue is, how do we start the mix design process? What kind of tests do we use to select these kinds of, to get the right kind of characteristics in my mix design? What we've shown with this work is it is possible to recommend a suite of tests for the evaluation of printability, irrespective of the binder type used, because everybody is comfortable with using different types of binders. We have to use cement extenders to reduce the impact of OPC or ordinary Portland cement usage in 3D printed systems. Now, one thing obviously is that what is clearly seen in 3D printing literature is that the binder properties that are, or mixed properties that are required often depend a lot on the material, on the printer characteristics. Now, what this set of studies goes to show is that by evolving the right range of combination of parameters through these systematic tests that I've just described, you can actually fit the needs of any different combination of printer and printing material. And again, the systematic approach makes it possible to design 3D printable concrete when you have alternative binders and aggregates without really doing too much of sophisticated instrumentation work. Most of it is laboratory equipment that is easily available in most civil engineering labs. So thank you all very much. I'd like to also share that much of the work that I've shown here is part of the Center of Excellence in Technologies for Low Carbon and Lean Construction that is here at IIT Madras. I urge all of you who are interested in collaborating in approaches that can bring down the overall carbon footprint of concrete and also ensure that we have more sustainable practices adopted in construction with concrete. I welcome you all to collaborate with us. We have a lot of work that is going on, not just with 3D printing, but also with construction demolition waste, lean construction, optimization of resources, so on and so forth. So thank you all very much once again.
Thank you very much, Professor Santanam, for this great presentation. We have a question in the chat box. So is it possible to separately quantify the contribution of aggregate matrix and binder paste on structural buildup or buildability?
Yeah, I mean, I don't think we've done the parametric studies to really separately quantify the contribution. But I'm sure that we could do this by adopting certain models for particle packing for the aggregate matrix, and then using the different binder systems that exhibit different rheologies to really get a better control on how do we actually quantify this effect of packing of the aggregate, and how do we quantify the effect of the rheology of the paste itself. Yeah, we've not done that yet, but I'm sure that this approach can be actually used towards where.
So the next question is a bit more general. So it's if our 3D printed concrete structures safe under impact loading? I don't know if you can answer that question at this stage.
So I'm hoping that some of these questions will also get answered when we look at the structural side of 3D printed concrete, which will be talked about in the subsequent presentations. Now, of course, with impact, it's only one type of load. Structures are subjected to all kinds of loading. So as long as the structural design is able to take care of it, definitely we can actually design 3D printed structures for impact also. Uh, you have to just remember that it's not we are not changing the construction technology, or rather construction design. We are only changing the technology in which we are delivering the concrete. Rather than using a formwork, we're simply printing it in the right form. If you have to obtain special performance against special type of loads, obviously it has to be designed into the structure. And we have seen that we can actually even design concretes for earthquake resistance with suitable performance, as you'll see in some of our subsequent presentations.
Yeah, so basically, we all know that at highest strains, the material behavior is different than
Yes,
just a static loading. So it will be interesting to see how anisotropic behavior of 3D printing will affect its behavior at highest strains
exactly.
under impact loading. So the next question, can Brookfield viscometer be used to study rheology of paste instead of rheometers?
Yeah. So yes, Brookfield viscometers can definitely be used to study rheology of paste, because Brookfield also has the vein attachment which can be utilized. A lot of the studies initially that were done on cement paste were using Brookfield only. But the issue is there is a limit to which you can assess the quality of the paste and use that to actually predict the rheology of the mortar. In this case, it's a mortar, although we call it concrete. The connection is not that straightforward, but yes, it can be established.
The next question, are there any other tests that needs to be done to check material suitability?
The material suitability for 3D printing, of course, I've mentioned the tests that you do after the concrete is prepared. The material suitability also includes selection of the aggregate properly. So the grading of the aggregate is obviously very important. You also need to look at the overall particle packing of the system, because you're using finer mineral additives also. So overall gradation, including the fines as well as the fine aggregates, needs to be checked properly. So material selection obviously includes understanding of what level of strength you're desiring in your system, and choosing a water cement ratio adequately. The problem obviously comes when designing 3D printing, that you don't really have a control to use very low cementitious contents, because getting the right kind of characteristics for rheology needs you to adopt a higher cementitious content. So that's one thing that you have to look at carefully.
Um, so the next question, are there any tests to assess the potential shrinkage in 3D printed concrete?
Uh, yeah, shrinkage can be tested also, but of course that's a property that comes into play once the material is deposited and it's in service. A lot of the early age shrinkage issues can be seen quite uh, quite a lot in the 3D printed concrete, because you don't have anything protecting the surface after it's printed. So you have early age drying, which can cause shrinkage. Measurement of shrinkage can be done to establish uh, the requirement of conditions during printing that will reduce the impact of drying. So a lot of shrinkage happens because drying happens almost immediately after the material is printed. You can't obviously resolve that problem by using expensive shrinkage reducers all the time. You have to ensure that you work in an environment where the concrete is at least protected till it attains a significant amount of strength, so that shrinkage does not result in cracking. But yes, shrinkage cracking is a huge issue with 3D printed concrete.
Maybe our last question, which needle is recommended to study the penetration resistance?
Now, when we are talking about 3D printed systems, we are talking about mortars. So it's always better to use a penetration resistant system rather than a bicat needle, which is more suitable for paste. So again, relating paste directly to concrete, you need to have some level of understanding as to how the behavior is changing from paste system to a concrete system. So I'd rather work directly on the mortar with the penetration.
Okay, I think we need to move on to the next presentation. So if you have any further questions, please contact Dr. Santana
Yeah. So
after the session.
while you continue, I'll just also try to answer some of the chat box directly also. So not a
Sure,
problem. Please go
perfect.
ahead.
So again, thank you very much, Manu. Now we will move on to our second presenter, who's Dr. Srikanta Das from University of Windsor. So Dr. Das, if you can please share your screen. Dr. Das is a full professor at the University of Windsor, and he's going to talk about the state of 3D construction printing in North America. So we can see your screen, Srikanta, and if you can just put it in the full screen mode.
I'm not very good at the Zoom, so I'm trying to figure out how to share the screen.
That's okay. We still have time.
Yeah. Give me 1 second. I'll be okay. Give me 1 second. We don't use Zoom that much, right? So.
Yeah, and sometimes it's difficult when you have multiple screens to find the right screen to share.
Yeah, so how do I find my screen? That's the thing I'm looking at. I know I had it then.
So when you click on share, it basically gives you all the screens that you have. It shows you all the screens that you can share. So are you using a single screen or you have multiple screens, multiple
single
monitors?
screen. I had it, but I don't know where I lost my, give me a second. I lost my presentation. Yeah, we don't use Zoom in so much, right? So if I go share now, do you see my screen now?
Yes, we can see your screen. It's not in the full screen mode, but we can see your screen. So.
Yeah, I'm going to change it. Do you see that now?
Perfect. Yeah.
Okay. Give me 1 more second, okay?
Sure.
Okay, let me know when I can start.
You can start.
Okay, thank you very much, everyone. Vaid. My presentation will be a little bit on a high level, not getting into too much technical thing. Again, I love talking, so if you see me, I'm going over time, don't be shy to stop me on, say, Srikanti going over time. So anyway, my discussion topic is the state of 3D construction printing in North America. Even though it's North America, I'll also talk a little bit outside of North American things happening. So my name is Srikant Das. I'm Associate Dean of Research and Grad Studies in the Faculty of Engineering at the University of Windsor. So this is my discussion topic. It's going to start about what is 3D printing. I know most of you already know, Dr. Santanam already talked about that, so I'm not going to spend too much time on this. Some projects in North America mostly is the US and Canada. I didn't see much from Mexico, even though Mexico is part of North America. I'm going to talk about and brag about the Canada's first 3D printed residential housing project, which I was the one who executed the project with Habitat for Humanity. Then other landmark projects going on in US, Canada, and also elsewhere in India and Europe. So what are the research we're doing? I'm primarily a structural engineer, even though I do a little bit of material research. So my talk will be focusing primarily on structural side and also building envelope side. And what we're doing, what is our future direction at the University of Windsor? That's what I'm going to talk about. So as you know, Dr. Santanam talked about 3D printing is a layer by layer construction. There are a few things you have to be careful. Pumpability, buildability, and all of this. So I'm not going to talk about that. It is a digital construction approach. So this is a digital construction approach. I call it partial automation, not full automation, because it doesn't do full automation for the construction. So we need more automation into the construction industry. So advantages and challenges, most of we know, there are a lot of advantages, but any technology has challenges. This one also has challenges, right? It's faster and cheaper. It requires only 3 construction people instead of like 15 people to do the construction. It minimizes the injuries and death in construction site because it's the robot primarily involved in doing the work, not the human being too much involved. It is better for environment because it reduces the construction waste, less pollution, on-site construction because less equipment involved and less noise, less fume, and all of this. It provides the architectural flexibility. Architects love it because you can print a castle with this, right? With no additional cost. It can be combined with other type of construction, can be used as modular or offsite construction as well. I know people have been doing this. The challenge is, okay, it's a new technology, needs a new skill set, and we need to train those people required for this technology. So building codes, as far as I know, there's really not solid building codes anywhere in the world. I know Marcos, who is going to be one of the presenter here, is my PhD student, was my PhD student, not anymore. We've been working on the STM code. We did one, we're working on the second one. I know SCI is also parallelly working on other code. In Canada, we have started talking about our old building code on 3D printing, but it hasn't started yet. So other issues that awareness among the engineers, builders, city professionals, and this technology is there, but civil engineering profession has a hesitant. That we are hesitant to take a new technology. We need to train them the benefit and how you do this. And of course, the research funding is always an issue everywhere in the world, and we also face that challenges. Government policy, we're going to talk about a little bit on that. So there are many projects has been done since the first project was done. On the left screen, you see this is a project where we did, like Marcos was my PhD student back then. He was the project manager, but we did it with the government funding from Canadian government in collaboration with the Habitat for Humanity. So you see it's a 4 units, 1, 2, 3, 4. And the back, you don't see that, but there are 2. It's a small house in it. It's like a 1-bedroom unit for, people who has the financial challenges, right? Print time was very, very small, even though we had interruption because there was the first project. We were learning a lot. So 2 weeks for all the walls been printed. Project duration was from April. We started in September, was done. People moved in October. That was pretty quick. I thought this is amazing because if you use the regular construction technology, it's going to take at least 1.5 to 2 years. We cut it down to 5, 6, 7 months. We use Cobalt Board 2 printer, which is a gantry style printer. Cost was 220,000 per unit, which is like 550 square feet, which is comparable with the current other construction techniques. So we did not make much cheaper, but we did not make it expensive. We wasted a lot of money because of the new project. We didn't know where to start from and how to finish that. This project is located in Leamington. It's a small town near Windsor, and that's where it is located. But this is the first project done in Canada. Since then, the company who was involved is called Nidus 3D. They have printed a few other houses. I know Marcus was there and back then, and there's a 2.5-story house you see on the right skin. With the basement is the 1/2-story and 2-story. So it's basically, we can say 3-story, but it's a 2.5-story house. Total area 8,740 square feet. The print time was 30 days. Again, it's the same printer was used to print this. So the other houses, again, Nidus 3D has printed similar to the house we printed in Leamington. They printed 4 of them. In near Calgary is for our indigenous community called Siksika Nation. So that's the housing for them. Was done in collaboration with the Calgary School of Architects. It's 1 week per building print time, and it was done in fall winter, so they have to have the encasement, so on the heating inside. It's the same printer. It printed the house. The cost was 180,000 per unit, which is, I find, is cheaper than what we could do in here, right? So the bigger project so far in Canada is this one. You see on the right side, it's not completely printed. You see these walls are printed, but then everything in between is a glass panel. And the second floor is not printed. To me, it looks like the timber houses, right? Second floor is just a regular construction. I don't know the details because there's no information you can get from website. This is my understanding. That second floor does not look like it is printed. It is just a timber house. I might be wrong though. So anyway, it was 15 months. And they're going to open that up in fall 2025, September, October. So they make 226 of those houses in a row. Again, they have their own printer, robotic arm printer. I don't have the details because there's no details I can find from anywhere. So they say the cost was about 300,000 per square feet, which is decent in terms of the cost. Coming to US has done a lot. So the first project in US was this one. Again, the Habitat for Humanity in the US, they did it. So it's 1,200 square feet bungalow in Virginia. This is the same printer, bought two printer, printed the house. Then there are bigger projects going on. During the pandemic, I would say the Europe was the leading in the construction in this technology. Now I think it's the US is the leading. They're moving very fast with the technology. So they're printing the whole communities. This is one of the community they're printing, 100 homes. They just completed that. That's the largest 3D printed community in the world. So each house is like 1,500 to 2,000 square feet, which is pretty big. 3 weeks per printing. It's icons, their own printer they use. It's a Gantt style printer, but there's a unique printer they have. And they use LavaCrete is their proprietary material to print that. The cost, again, is 430,000 US dollars, so which is decent, as the location is Texas, Georgetown in Texas. But stop me if I'm going over time, okay?
You still have time.
Okay. The other projects, you probably know about this one on the left. This is the Mars Training Center or simulator, which is 1,700 square foot, printed by Icon again. Icon is the big player in the US. I see they have their own printer. I don't think they sell the printer. They use their printer for their own business or own construction. So they printed in 3 months for all the walls. It is a beautiful building. It looks like it is in Mars. They use the color to match with the Mars color, right? Icon Vulcan printer is the LavaCrete. Again, this is a very proprietary material they use. It's not the regular cement concrete they use, right? It's located in Johnson Space Center in Houston, Texas. Then the other community has been printed. The first community, larger community printed in the US is this one on the right side. This is in desert in Palm Springs, California. So you see, it is a very high temperature, right? So that's what they did. They did it in an offsite construction. So they printed all the walls and then brought it in. They stacked it with the steel modular frame. Sorry, steel frame. That's the wall was more like an infill walls, right? So it's a very luxury home. Those are the luxury home. There's not a cheap home. And the Mighty Building is the company build those houses, and they use, I don't know what printer, but I know this is a Gantt style printer they use in their factory. Each home is about 1,866 square feet. It is a luxury home. It has a swimming pool. It has solar panel. It's a beautiful home. It's middle of desert, right? So you see the cost started from $1 million US dollar. That's an expensive home. So of course, it is an expensive home because it's a luxury home. So other non-residential projects going on as well in the US and elsewhere in the world. So you see the left one is 10,000 square feet single, so it's a barn, as a farmhouse. I think this is the largest 3D printed structure, in the world. The project was done in 9 months. This has modular roof though. Roof is not printed anywhere in the world as far as I know. They use cobalt board to print the one I used for our project. It's located in Wellington, Florida. So this is a huge, huge project. Then recently, Walmart has taken this technology to demonstrate the sustainability in the construction. These are the big players. They are the one who needs to take the lead on any technology. And I think Walmart has been very progressive on that. So they are using this technology to build one of the warehouse in Athens, Tennessee. It is a 20 feet high, tall building. It is a warehouse, so it is a bit tall. It is located, as I said, Tennessee in Athens. Alquist is the company. They using their 2 robotic arm printer. I don't know what kind of robotic arm printer. All I know from the news, they use 2 robotic arm printer at the same time, 2 different locations to print this. Print time was 45 days. Project delivery it was delayed due to the fogging and the heating. That's what I found from the internet, but I don't know the details because these are the commercial project. They don't publish too much information on this, right? Their goal is to becoming more environmentally friendly. So these are some of the projects. Okay, there are other projects going in the US. This is not the everything I talk about. There are other projects going on. Same thing, the Europe, as I said, in the pandemic time, I've been working on 3D printing for the last 5-6 years, me and Marcos, right? So when we started working, I thought that the Scandinavian country were the leader in this technology, and the Europe, like Germany, Italy, France, were the leader. They're still doing well. I think the USA is taking over everything. They're doing in a big scale project and so on. Anyway, the one on the left, you see 6,600 square feet. It is a data center in Germany. It's a telecom company in Germany. It's done, printing house done in 140. It's a beautiful carve house. You see that. It's a wave design. Of course, they use cobalt board printer, was similar to the one we used in our housing project. It is the largest 3D printed building in Europe. So then Italy is a company in Italy. They used to print by printer. Their printer is very different than other printer. They use more like a crane and the boom. So these two printers at the same time to print display houses. I'm not quite sure whether anybody living there, but it's beautiful house. You see the roof is the glass roof and the door is a glass door. Everything else is printed up clear. This is why we should be all going, because this is more really sustainable, right? The other project, as you are from, if you are from India, you know, India recently printed a post office. It is a cobalt board printer. I think it's a similar printer we use. With the L&T is the one who built these houses. It is printed in the construction time is 23 days. I don't know whether that means everything. I think this is just a probably print time. I'm not quite sure. You know, this commercial project, you don't get all the information from the website. They don't provide all the information. So you try to get one information on one side, one information on other website, then you try to mask them. You don't know exactly what you're collecting, right? So don't trust everything I'm saying when it is in a commercial project. I don't know. They say cost saving is 40%, which is amazing. Saving in the construction time is 80%. You know, that is probably, I don't know, 80% saving construction time is too much to me by doing a project. So this is a beautiful house, a villa printed in 2023 in Saudi Arabia. It is the world's first 3D printed 3-story high building. Total area is 3,714 square feet, printed in 26 days. It doesn't mean her project was completed in 26 days. Printing is done 26 days, but I don't know how many months it took to finish everything else. Again, they used the cobalt board to printer, the one we used for our project. The other project, this is when I was in India. I just got the news from the media that Tavasta is one of the leading printing company in India, or printer manufacturing, and also the construction company in India. They printed a 2,200 square foot 2-story high villa in Pune, which looks beautiful. It's a carved wall. I don't think with the traditional technology, we would be able to build this kind of beautiful structure. So they did it in 4 months. Cost is 5 lakhs. They say it's 20% cost of a flat. I don't know what that means. Again, these are the information I'm collecting from the different website, right? Tavasta used their own gantry style printer to print that. So China has been a long time ago, multi-story apartment building. You see that on the right. But this one was printed. It's an offsite construction. They printed the wall in a factory using their gantry style printer. The company name is Winsun. It's the largest company in China. They have a huge factory. They print all the wall, they stack it, and they build as a modular construction. But they are the one who really was doing very well in 2015, 2020. I don't hear much from them anymore, but they're the one who was leading once upon a time. So, as I said, if you ask me that question, who are the leader in this technology, I will say, Scandinavian countries were the leader in 2020s, not anymore. Europe was the leader, not anymore. Maybe the US, the one was the leader. Canada is catching up, but Canada is not doing well. India is doing okay, and other countries are doing okay. So you see the ambition people are doing. They're saying, okay, like Saudi Arabia has a mandate to do 25% of new building to be 3D printed by 2030, which is a bold move by Dubai. And I think
Dr. Das, sorry, I'm interrupting you. So you have 1 to 2 minutes left.
Okay, no problem also. And then Saudi Arabia is doing that same thing too. This is the project we did. I'm going to go very quickly on this. As I said earlier, that the cost was kind of the same as the traditional printing. This is the construction phases of different picture. I think Marcos might show some of this picture. This is what the structures lab, we're doing a lot of testing. I'm a structural engineer. I do material testing, but mostly the structural testing. I don't want to show my lab because I don't have time. This is the material testing we have been doing, and we published a couple of papers, but there's some on pipeline and being processed. We're doing all kind of tests. Then we're doing a lot of full-scale tests on different configuration of different tests. Some of the thing I want to do is to show you, this is the wall we tested without the reinforcement. You see, we only don't have reinforcement, it's catastrophic. Then when we add reinforcement, you see it fails. It goes a little bit higher capacity, but also give me the ductility. It doesn't collapse completely. We tested a wall with the lintel, of course, there's reinforcement, you see it's a catastrophe, right? So these are the full-scale wall, like 2.4 meter half. So we are also doing building envelope tests, so rainwater penetration tests. So we have a chamber for this full-scale test. We have the R-value thermal resistance test. Canada is a cold country. This is a concern. So we need to make sure that 3D printing building can hold the temperature inside the house. We're not going to get the thermal breaching. So we're doing that too. So these are the tests we done. This paper is under review now. So we got up to 17.7 R value, which is what we need in this area of the country, right? So we are good to go with this. And what we're doing in future, we're gonna do a research center. We have a research center. We're gonna expand that. We're gonna push the government to change the policy to adopt this technology, training the new skill set. As I said, we need new skill set and awareness among the people. We're doing all kind of material research. This is my target in the next 5 to 10 years. We don't have to talk about everything. Again, I'm not a materials engineer, but I do a little bit of materials testing. So this is my big time goal. So not only building the houses, make the houses net zero and sustainable, so including geothermal energy, solar power, modular reactor. By the way, I am in the process of building another house soon. If we get that house, that will be one of the iconic projects in the world. Thank you very much. Sorry if I took too much time.
Thank you very much, Dr. Das. Very interesting presentation. I wish we had more time so we can talk about the second half of the presentation, which was about those interesting experimental work that you have done in your structural lab. We have two questions. The first question is, could you please explain the execution of multi-story 3D printed buildings? Basically, when we go from one story to multi-story, what are the challenges and how do they do the construction? Do you have any comments on that?
Okay, I haven't done any multi-story project yet. I'm in the process of doing one soon. But that hasn't started the project. But what I hear from other country or other projects, like Marcos can talk about that when he talks that he did 2.5 story. I don't think there's any challenge. If you do bring a big gantry style printer, which can go up to high 3 story, then there's no issues. Only thing issue is that when you lay the slab in between, you have to bring the hollow core slab before you go to the next floor. So Marco can talk about that. But if you do multi-story using modular, like the Chinese company did that, then that problem is different issue. Then it's a modular construction. You build all the walls, you bring the big crane, you stack one with the other one, then your connection becomes the major issues, right? Not the really construction, is the connection between the wall and between the column and the wall, between the beam and the column. That's the issue, becomes major structural issues, right?
Okay, so the next question is so let me see. Did you use any local materials in 3D PC mixture? Basically, I think in the structures that you showed that was built in Canada, they use local material. And then the second part of the question is, can the same house be built in Northerner Canada because of the extreme weather conditions?
Yeah, so I forgot to mention that because rushing, I know I don't have much time. The house we printed using regular concrete, not the paste. Not the cement paste. We use the aggregate up to 10 millimeter. And we use our local aggregate. We did not use any proprietary material. I think this is the first house printed using the concrete in the wall. So it is a local material, yes. And it's a concrete, not mortar.
So I guess we have still some time for a few other questions. So as the layers of concrete are laid, what are your points of view on the bond between two layers of concrete? So the interlayer bond between concrete layers.
So for interlayer, when you mean when you finish the project for a day, then you come back next day. So we have special proprietary treatment. I don't know whether I'm allowed to talk about that. So Nidus has their own proprietary mix. It's kind of a paste. They'll put it on top of the yesterday's wall, which is kind of now hardened, not fully. So and then they put that, then they go for the next wall. So we did some tests on those, and the paper I think is coming up in SC journal soon. It's been in the production state. So when this is out, that I didn't discuss what the paste is because that's proprietary. But I use 3 different treatment. One is the paste, one is just our own cement paste, which is like nobody told me what to do. We did that. The other ones, no, nothing in there. So that paper will be out soon in a month or so.
Okay, thank you. So the last question is, what is the thermal conductivity of the material for the wall in which you are getting very good R values?
So it's not the wall, really. Wall, you have to remember this, the material we use is just a regular concrete. There's no difference. It's not a fancy concrete we use. I don't think the R value will be different from the material. What is the difference is the insulation. In Canada, your house must have insulation, right? So we have 2 wall going parallel. In between, we have 5 inches gap. So in the 5 inches gap, we use high R value insulation. That gives you the enough R value you need. Now, the house we're going to print, Marco probably will touch on this as well, which we are working, Marcos, and we are working on this. That will have even 40-inch, no, Marcos, correct me, 30-inch probably wall because we wanted to make net zero housing. So our value will be 35, 30, 35. So you can adjust that width, you can adjust the material inside, you can put the different insulation material. It's all up to what you need, right? So no, material we did not test because the material is the same material. There is no difference between regular concrete and this one.
Okay, thank you very much, Dr. Das, again.
Thank you.
We need to move on to the next presentation. I see that there are a couple of other questions in the chat box, so you can reach out to Dr. Das, and I'm sure he will be happy to answer your questions. So our next presenter is Professor Subramaniam from the Department of Civil Engineering at the University of IIT Hyderabad. Sorry if I'm mispronouncing your name. So Professor Subramaniam is going to talk about the functionally efficient form optimized structures for concrete 2D printing. So the floor is yours, Professor Subramaniam.
Sure, thank you, Wahid. Let me start by sharing my screen. Okay. I hope my screen is visible.
Yes, we can see your screen. If you can just please put it in the
screen. There we go. Okay, fine. Is
Perfect.
that better? Okay, great. Thank you, Wahid, for the introduction. Let me introduce my team. We have a whole team, a printing team at IIT Hyderabad. Basically, it comprises of my students. Then, of course, we are teamed up with a startup called SimplyForge Creations. I have a structural design consultant, and we are working with the Indian Army for developing these functionally efficient, what I call form optimized concrete 3D printed structures. So now here is the motivation for the work, and that is our current form of construction. We rely on rectilinear forms, and what slows us down is this whole process of assembling the formwork, putting in the steel, casting concrete. So one, we are limited in shapes to rectilinear shapes, which are basically not the most efficient shapes. And what that means is we are using more material and not being efficient. And where in structures where dead load makes up, say, 70 to 80% of the total load, it just adds up, and that's just not worth it. So, and of course, this form work is another limiting factor. So, of course, what we want to do is get to something what is shown on the right-hand side here. If I can just enable my pointer. Where is it? Yeah, so what we want to show, we'll get to is something of this form where we want to do form-free construction, basically dream up something and print it in real time, where we are not limited by the form work and we are not limited by rectilinear shapes. And what we can do is get to this lean construction where we follow the principle of material follows force and get to form optimized structures. And that's what I want to demonstrate today. So what we wanted to do was actually deliver a 3D concrete bridge, and we want to do this and actually put our money where our mouth is, and actually demonstrate this concept of the bridge. We've actually printed this bridge. It is fully functional on our campus. It is a form optimized, where basically form specific structural optimization has been performed. And we've come up with something which is really lightweight, which meets all the performance criteria. And we want to get this experience of design by testing and document the entire design and evaluation process. And of course, a great exercise for students who are involved in it. The whole idea is that when you have a structure, when you're 3D printing it, it's an assembly of filaments along predefined contours in a structural form. So what we do if we go along the process is first, of course, development of the material. And I think Manu talked about it in the first presentation. We need a printable material and which exhibits buildability. That in itself has quite a good amount of challenge in it. The material is also called the ink in certain parlance. So, of course, I will not be talking about the ink part of the thing. What I'll focus on is this form optimized structural system where we basically are talking about this printing contours and assembling these contours in a form optimized kind of a shape, and the construction methodology. Right in the beginning, we said we are not going to do it on site. We will do an off-site printed structure, assemble it on site. Then, of course, we went through the process of testing and calibration and did the field deployment to the bridge. Now, the printing system itself, very quickly, we are using a robotic arm system. This is not a gantry system. We've developed a customized engineered pressure control continuous pumping system. Basically, this is a PLC controlled pump that precisely delivers the material. There's a nice synchronous movement between the pump and the nozzle, and we have a printing system that has throughput of about it can go up to 2.2 tons per hour. Then what we have is the printing platform. Of course, we've developed it, we've tested it. All the print variables were optimized. The material mixture, like I said, I will not be talking about it. We've developed it using local materials. I know there was a question. We can use the local materials. Now we have ways of developing systems that are materials that are printable in our system. And later on, I'll demonstrate where we actually took it to an extreme. Now, the material that we have developed, we tested it. And of course, when you talk about a printed system, you have to be very careful. It does exhibit directional dependent properties. So when you have a printed assembly of layers, as I've shown here, if direction 3 is my printing direction, I have 2 other directions which are perpendicular to this. So you have a direction which is basically perpendicular to the print layer, which is 1, and then 2, which is along the layer interfaces. And what you see is when you cut cubes out of this printed assembly, you'll find that there's a first thing is the strength in the 3 directions are different, and there's a good amount of variation. There's always a lot of variation that you have to account for this. So, of course, when you're doing design, you have to come up with a conservative estimate of compressive strength. You can estimate the characteristic strength. We've collected a lot of data. And for this particular concrete mix, with this kind of variability, we took the compressive strength as about 30 megapascal. Using this as our starting point now, we are talking about developing the system. Of course, you need to put in reinforcement. And when we were talking about a structural system, we wanted to use the simplest form of reinforcement, that is to simply put steel between the layers. Simply just add a bar of steel between the printed layers. And so here, when we had printed layers, which are themselves about 15 millimeters thick, 50 millimeters in width, we were looking at reinforcement in the form of a 3 millimeter steel bar, which is placed between the layers. This was tested in flexure. And when you test it in flexure, this is the kind of response you get. It's a very low reinforcement ratio. So you find that when you test it in flexure, this is a notched concrete beam. You see that the crack emanates from the beam. This is where the reinforcement was placed. Initially, the load drops, and then eventually, after a crack opening of about 200 microns or so, the load picks up. The steel actually takes the load, and you do get a load recovery, but that happens at a significantly larger crack opening beyond 200 microns. So Now we have the reinforcing system that we knew. So from here, then we could actually extract out the cohesive or the crack closing stresses that come from the steel, this which became a part of our design. And I'll show this later. So now let me focus on the development of the structural form. What you're seeing here is literally things that I've scanned from my notes. And as we were going through the design process, I was sitting with the design engineer, the design consultant. What we were thinking about was something which is in the form of a tied arch. So in a tied arch, what you have is a concrete compression arch, and then which is tied together by a tension tie. It forms a nice self-equilibrated system. And initially, we conceived a form of this form where the concrete arch would basically have all these elements here, which are basically the filaments, and the entire assembly would be held together with this tension tie. And the whole idea was to develop a form that would minimize tension in the concrete. Then the other thing is I want to orient the strongest direction of my material. The material is the strongest in the direction of extrusion, and that I want to orient along basically the direction of high stress, which would obviously be in the direction of the filament itself, as you see here. And of course, reduce the overall weight by optimizing the structural system within this compression form. So with these three objectives, we started. And the fundamental idea was to start with something which is like a rectangular beam. So we're trying to develop a bridge of a certain span, start off with the rectangular beam, and then arrive at the final shape following something similar to topology optimization, except here we're not following topology optimization to the T, because here we have certain constraints. The constraint is that I cannot vary my filament width. Usually we keep the filament constant, width constant. And of course, we have this constraint of orientation of the material, trying to keep it along the orienting the material along the direction of the highest stress. So this what we did is that's why a process that we call form optimization. And here what we do is, starting with this beam, you use the principal stress trajectories which are derived from which you get from the simple stress analysis of this rectangular beam subjected to a uniform distributed load. You identify the compression form. Basically, you see the top form of the concrete beam here is in compression. The bottom is essentially in tension. So you get this first cut of a compression form of a beam, so which is held together with this tension tie. This becomes the starting point. Now, form of specific structural optimization can be done inside this compression form, where basically broadly following material follows force principle. And then when I do this, basically, because this is already in compression, the tension within this compression form would be very minimal, and I can get away without having to use much reinforcement inside the concrete. Now, the whole development of the structural system follows the Mitchell truss philosophy, where basically what you do is structural form within the compression region is developed in the form of truss design from the principal stress trajectories. And what we do is we take the 2D stress field and replace it with 1D elements, basically a lattice design of 1D elements, which are broadly aligned with the principal stress trajectories. And doing this, the first cut, we came up with a 3-piece truss design for a bridge. So in this 3-piece, you have the first piece here, you have the central piece here. This would basically form like a keystone. And then you have the third piece here. The first and the third piece are actually mirrors of each other. And then you have the keystone that locks the whole thing in place. Now, if I do this, then basically I can align my material, the material direction 3, which is the strongest direction, along the direction of the struts, giving me the advantage of having the strongest direction aligned where I have the highest stress. We do this analysis of this and we find something that is not unexpected. What we have is that these diagonal elements that form these the struts and the ties, basically they alternate in compression and tension as you would expect. So they form struts and ties within the structural form. And the top chord here, you have the local bending effect that happens here. So this top chord itself has a predominant bending effect. So you do get some tension at the support and the middle between the supports here in the top chord. So that's where we should expect to put in the reinforcement. Now, the other thing is we have these 4 and 5 member intersections like what you see here. Now, these create problems from print geometry, because if I have this complex junction, then I would actually have to lift my print head even to finish the contour on one plane. Therefore, these are highly avoidable. So the next round of iteration, we said we'd go to a two-piece bridge, where basically you have these two pieces which are held together by this keystone that is cast later. And when we do the analysis, basically we find, not surprisingly, the alternating compression and tension struts and ties, and the top chord goes into tension. Now the form was further evolved. So the first thing is to make the arch a little deeper. That basically increases the level of compression, reduces the level of tension. And by doing this, we were actually able to reduce the material by 13.5, by almost 13-14% compared to the previous iterations. Now, going further further iterations were performed, keeping the compression form, that is, you see this compression form on either side the same, and basically playing around with these struts. So now this angle, this angle between these struts is what we varied and came up with a form optimized structure that you see here. Now here, as we are varying, what we found is that the self weight decreases as I decrease the number of members in my truss, and that actually contributes to a reduction of stress more significantly than the increase in the span or the length or the geometry of the members. Now, but what happens is, if you look at the top member here, if you compare this with this fellow, as I increase the spacing between these elements here, then the bending stress starts dominating. And at some point, what happens is that is the break-even point. And that's where we essentially stopped, where the tensile stress in the bending element started becoming very significant. So with this, we came up with this form optimized shape of this bridge. This bridge was, we were not directly ready to print it. So what we did is we first printed a smaller prototype bridge, which was of a 5.4 meters length and 1 meter in height. This bridge was actually offsite printed. We assembled it, we load tested it, and you see the load testing of this bridge. This is the load displacement response of the bridge, which was instrumented. And of course, we were able to calibrate our numerical model. So what you see here, this is a simulation of our finite element model. So that gave us confidence that our finite element model could actually predict the deflections of the structure. We had confidence in prediction capabilities of our bridge, of our modeling system. Then came the actual bridge. It was a 7.5 meter bridge. It's a two-part bridge that I'm showing you here with the closure pore here. This is the reinforcement template. So we basically prepared a template, and one steel template, which is basically a 3 millimeter wire, which was essentially bent and spot welded in the shape, was lowered immediately after one layer was completed. And we put one of these steel templates between 8 layers. That basically gave us a reinforcement ratio of about 0.1%. Now, we did a finite element simulation to predict the final load capacity of this. Here, of course, we have the cohesive crack closing stresses from the fracture test as to what is the crack closing stress provided by the reinforcement. We have the behavior of the concrete, which I did not present here. We have the full nonlinear behavior that we were able to get. And from here, then we were able to predict the load response, where the damage initiates. Initially, you see tension damage initiates at a lower load. Then once you go to load point 2, you see that the damage actually grows. You have a lot more tension here. Damage, which is basically the top chord cracking in tension, but the reinforcement steps in. It's able to take the load. Then final failure, you see, happens at a very high load, which is about 220 kilonewtons. And this is when the compression strut essentially fails in compression. So that is what produces failure of the bridge. And we found that the failure happened at a very high load, significantly higher load than what we had expected. This is just a short video to show you the printing of each segment. Hopefully that video will work. Well, let's, yeah, so this is the video. So you see that it's relatively fast for us to print each layer. The entire bridge was printed with a total printing time of about 6 hours. The 2 segments were then brought on site. They were essentially assembled. This is the final bridge. You see the 2 segments here. This is the closure pore here. And of course, we had to put a deck on top of it because the rippled surface made it tough to walk on because this was designed as a pedestrian bridge. And the only thing where we've cheated a little bit is we didn't have data on fatigue. So we had to take a stress reduction for the fatigue loading. And this is, of course, one of those things. And of course, we have a bridge which is 7.5 meters in length, reinforced with conventional steel in the form of a continuous steel bar. It's offsite printed and it's erected. It is fully functional, designed as a pedestrian bridge, but can actually take much, much higher load than what it is designed for. Now, lessons specific to the project, what we have is that we have to learn to link between the physical form, the digital representation, and the model representation. There are a lot of things that we make. We do a lot of hand waving here. We still don't understand the leap of faith that goes in from the physical form to the digital representation and the model representation. A lot of unknowns in especially the model representation part. The mechanistic understanding of the system response is still something we're grappling with. We don't have a full handle of it. Continuity between elements. So when we talk about an element like this, when you have a V joint here, what is the exact stress transfer that is happening here? And this is a model representation. But if you actually look at the physical representation, the material actually kind of bends here. When you have a flat element here, this material bends here, and it's just literally a wet contact between the two elements there. And of course, what we'd ideally want is the automation of reinforcement placement. What we did is we cheated. We put a template between layers, and that's probably not the best way to do it. And of course, fatigue performance, particularly for structures like bridges, is a big thing, big unknown in this particular case. And what we need is that we realize we need expertise in multiple domains when we've been talking about delivering a real life structure. Now, I'll switch gears and talk about something slightly different. And this I put in this slide because there was a question on BLAST. So we're working with the Indian Army on developing this form optimization further. And we're actually printing bunkers for them. And you see this, the shape that we've given here, the outer texture has been form optimized for blast and ballistic protection. Now, we've taken this printing exercise and actually printed a bunker on site at a very high altitude, about 4,000 meters. And this was done on site. We delivered a bunker, and this was actually ballistic tested to ensure that it performed far superior to the conventional bunker that is currently used. And perhaps we can claim the credit of the world's highest in situ printed structure at this point of time. Now, the other thing that I wanted to point about is the in situ printing of a medical facility. This was something that we've done again for the Indian Army. It's an integral hybrid structural system. So what that means is that we have conventional reinforcement. So you leave places for conventional reinforcement integrated with 3D printed walls. And then, of course, the roofing system is in the form of a sandwich panel, which is integrated with the reinforcement that you have for the structure here. And we're able to create a structure. This entire structure is about 1,850 SFT square foot structure, which was printed in about 14 days of printing time, and using a robotic arm, which was basically a movable kind of a system that we were able to develop. So with this, I'd like to close my presentation. Thank you for your attention, and I'll be happy to take any questions. I hope I'm doing okay on time.
Professor Subramaniam, yes, you're right on time. So we still have time if anyone has a question about this project. It's really impressive to see how much progress India has made in this field with all the different types of structures and optimization. So we have one question. What's your view on using graphene as a SCM in 3D printed mortar for bunkers? I don't know if the question is clear.
Yeah, graphene can be used. I mean, there's no issue with using graphene. But the whole idea of 3D printing structures is to take advantage of the technology and actually get away from this conventional mindset, where if you can use concrete to its natural advantage, where it is strong in compression, and like what we did here is keep the steel separate. And that way you get functional structures where you don't have to really think conventionally, where you're thinking about putting steel in with concrete. So this whole concept of using graphene and other expensive materials would have to be looked at from a cost and a functional improvement point of view, as to what improvement do I get, and is it really worth it comparing the cost of this technology? Because I think as Manu pointed out in the first presentation, the material is expensive at this point of time. And even in the second presentation, we saw at this point of time, it is expensive to print a structure. So I'm not breaking even if I'm not giving you some savings in the form of form optimized structures where I use less material. So that is the game that we have to play. And therefore, using more expensive additives would really need careful consideration as to whether I'm really getting my bang for the buck.
Okay, thank you for your answer. So the next question is, how can AI ML can be collaborated for this project on 3D printing?
Yeah, actually, that's a very good question because that's something that we are currently working on. And in fact, I think, I don't know if my slide is still visible, but if you see the scales that we have, the physical form, the digital form, and the model representation form, this is best scaled by AI. If you can bring in AI systems that can basically take a model and then quickly visualize the physical form, do a model representation, do an analysis, and in real time, while it is printing, it can do whatever modifications is needed to the material, then what you have is a system that is custom designed for this automated constructions that we are talking about, that is 3D concrete printing.
So the next question, what software did you use for structural analysis simulation? That was actually my question too.
Yeah, that is all done on Abacus.
Okay, so so the software was Abacus. In the literature, we have seen the merging conventional and 3D printing method is more costly. Can you put some light on the cost of the structure for Army?
Yeah, I mean, I can give you an example of the cost that we have here. So if you look at the bridge, what we did is we designed a conventional bridge using regular concrete, and I did a pretty dumb design of doing a rectangular beam. I said, let me take a rectangular beam of 7.5 meters and put, subject it to pedestrian loading as I would be required, and for a width of 1.5 meters on that with a deck slab on it, and kept that as my baseline. I didn't present that here. Compared it to my bridge that I get from the printing. Now, I found that there was about 40% saving in the material with this bridge that I've printed. My weight of the bridge is about 2 tons, the printed bridge. And but where I made significant improvement is in deflections. Because of the arch shape, there's hardly any deflection. My deflections are less than a millimeter for the full loading on the bridge. Whereas for the conventional rectangular beam, the deflection was about 11, 12 millimeters. And that is significant. So you're getting functional structures which are very stiff, and you're playing with the material geometry, putting it where it's required, and getting these functional designs that are very efficient.
Thank you. So it's interesting how much deflections is reduced. The next question is about your finite element model. Have you used cohesive elements for modeling the interface?
Yeah, so what we did is actually we extracted, or we've developed subroutines to determine or extract the cohesive stress response of the steel or the crack closing stresses provided by the steel reinforcement, and then inputted them into Abacus as the cohesive property of concrete. So that's what we have done for this exercise.
Okay,
so directly we didn't use the cohesive elements.
For modeling the interface between the layers?
So in this particular case, we did not explicitly model the interface. The reason is because I have already I'm considering the lowest compressive strength where the directionality is already accounted for. And when you look at this geometry, and maybe I should perhaps show the results of the analysis. So here, if you look at the geometry and you look at the tension in the perpendicular direction, this is where the interfaces are. The tension is negligible. Most of the tension is in the plane of the truss. So, and there we have reinforcement. So that's, again, the beauty of material, how you align your material, and you align your material in the direction where it is needed.
Okay, thank you very much. We have a couple of more questions. Please reach out to Dr. Subramaniam, and I'm sure he will be happy to answer those questions. Thank you again, Professor Subramaniam. Very impressive work and exciting projects.
Sure, thank you.
So we'll move on to our next presenter, which is from Canada, Dr. Marcus Silveira, who is the Director of Engineering at Printera. Marcus, Could you please share your screen? So Dr. Silveira is going to talk about the development of Canadian standards for additive construction.
All right. Good morning. Good evening to you guys in the other side of the planet. Thanks for having me here. I'm going to talk about development of Canadian standards for additive construction. Of course, I'm going to need to connect with the standards that have been developed in the other side of the border, right? Especially in the States, we have a few initiatives going on there. Yeah. So I'm not going to take too much time in terms of definition, right? So I would like to start this presentation with talking a little bit about additive construction. Everyone knows it's a layer by layer construction method. The term additive construction is being utilized, and the standards that we are developing are using that as the common language. We are trying to move away from 3D printing, so that's one thing that I want to bring here as well. So, and additive, of course, we are basing this term from additive manufacturing, and the difference here is just the scale, right? And scale, material, and everything, right? And everything that comes with it. So that's basically the definition, right? So I want to give you guys a little bit of an introduction of the regulation framework that we have here in Canada in terms of construction, right? So we have different levels, we have different institutions taking care of standards, building codes, and everything, right? So ultimately, we have CSA, right? So most of our standards, they're going to be published as a CSA, Canadian Standards Association. Those CSAs, I'm going to make some comparisons with the existing standards. For example, CSA 823 is the one dedicated for reinforced and pre-stressed concrete structures, right? So, and the same way we have a dedicated standard for concrete structures, we may have a dedicated standard for additive construction, right? So this is a way to see it, right? So we could have one standard dealing with additive construction in general, meaning that we would be dealing with cementitious materials. We would be dealing with metal materials being used in construction as well. So we would be tackling most of the materials that have been used in additive construction, right? Or another way to see it is incorporating the requirements for additive construction within the existing standards that we have. The CSA for example, for concrete, we would be putting concrete as an additive construction techniques applied to concrete, right? So there's a few ways to see it, but yeah, let's go back to the framework here. So most of the time, the CSAs, they're going to be referring back to other CSAs, of course, and also referring back to ISO's ASTM standards, right? So when it comes to testing, we have some special recommendations within the CSAs, but most of the time we are just referring back to ASTMs. And that's the reason we are putting a lot of effort on the development of ASTMs, and I'm going to talk about that later in the process here. Dr. Daz already mentioned a little bit about this, but I'm going to talk a little bit more. So also we have the National Building Code of Canada, right? So the National Building Code of Canada is most of the time based out of other CSAs. When it comes to concrete, when it comes to steel, everything, we are using CSAs for them. So again, just levels, right? And almost all provinces here, we have the provincial building codes. At some provinces that I had the chance to work, for example, in Alberta, they are, the provincial building code is pretty much a version of the National Building Code. Here in Ontario, we are based in Ontario, Printera. We are, I think I forgot to mention about Printera, right? So Printera, we are a company that does additive construction here in Canada. I'm the director of engineer of Printera. So we are based in Markham, GTA, Toronto, Ontario. So in Ontario, for example, we have the Ontario Building Code, right? Which is, of course, based on the National Building Code, but it has a lot more to just referring back to the NBCC, right? It has a lot of, I wouldn't say special requirements, but specific requirements for the province, right? But most of the provinces here, they are just using the national building code, which I think it's a very good idea, right? So, but those provincial building codes, they're based on the national building code, and of course in CSAs, enhanced ASTM, ISOs, and everything, right? And ultimately, we have the municipalities, right? When we are applying for a given permit, most of the time we're going to be applying that for municipality, especially when we are dealing with housing, right? So municipalities, they're going to be the ones taking care of those applications. And again, they are subjected to the provincial building codes, and on top of that, they have the municipal bylaws, right? So when it comes to setbacks, this and that, it's all municipal bylaws and not covered by the provincial building codes, right? So I want to show this. The reason that I want to show this framework is just to understand what are the needs for the industry in order to get to the standards for additive construction, right? Because I think everyone understands the importance of standards in every single industry, but in construction we have it's a little bit more than other industries because of course we spend a lot of our times inside constructions, right? Everyone here probably now is inside a building at this point. So as we spend a lot of time inside those buildings, we have a lot of concerns about safety, about, especially in Canada, we have thermal building envelope concerns when it comes to buildings, right? So the level, Dr. Does already mentioned this, but we are not super prone to new technologies, to new developments, especially because we rely too much on those buildings, on those structures, right? So standards are very important for this industry to really reach the mainstream, and we're going to be competing with other systems like frame construction, which is very popular here in North America, and other type of construction, right? So when it comes to international standards, this is a standard that we published a couple of years ago. It was a year and a half. Stefan Mansour, that I see that he's here present as well. He is the main leader of this initiative. Dr. Daz and I have been working on that as well. And as we are moving forward, we are bringing other specialists to contribute to the development of those standards. But this one we published in late 2023. We are most of the time we are just establishing nomenclature, qualification principles, and it's the first standard to open the doors for the other standards, right? So the ASTM groups that we have going on right now, there's a big list. I'm going to talk about just the ones that I've been a little bit more involved in. The one, and I just realized that the number here is incorrect. So the first one here is WK84415. So this is the one that I'm the chair. So I'm conducting pretty much the writing for this standard. Stefan Mansour, Dr. Das, and all of the contributions that we have here, they are also part of the development of this standard. The good news is that we are getting prepared to submit our document for voting in the next couple of months. So if everything goes very well, we should have this standard published by the end of this year, which at this stage we are covering compressive strength of cementitious additive construction components. So basically, we are using as a main reference, we are using the ASTM C1314. If you guys had the chance to work with masonry construction, you probably end up using that standard to evaluate your compressive strength, which is basically the prisms, the evaluating the compressive strength of prisms done by CMU. So we are using that as the main reference for the development of this particular standard. And we are, of course, addressing the specific needs for additive construction when it comes to layer height, layer thickness, and all of those things that are relevant to additive construction and in general, right? So with that standard published, we're going to have a standard way to measure the compressive strength of printed cementitious materials. Basically, this is more on the material side of things that we're going to be defining pretty much like the equivalent of the F prime C. And of course, those results are going to be used to assess the result, assess the actual strength against the specified strength that was provided by the structural engineer on the structural design. So there's a few other groups. So the one standard that we publish, it's being revised right now. So we are working on the review of that. That's the second that's the second item we have here. Other than that, we have other groups for materials. So this third one here, we are dealing with small cubes, small prisms that we're going to be extracting from those printed walls in order to evaluate and to assess the structural design that was provided in the first beginning, right? So the last one in my page here, it's about curing and extraction of samples, which is very important. We have another one which is about documentation, and we have the last one which is dealing with fresh and very early properties, right? All those four standards, the lead of those that develop those, the lead of the development of those four groups that we have here is Eric Krieger. He's an engineer for the Army, the USA Army. So they have done a lot of tests. They've done a lot of good research that they are using those results to convert into standards, which is very beneficial to our industry, right? Outside ASTM, we have other groups taking care of development of standards. Some of them are not enforceable here in Canada, as the ASTMs will be. But we also keep an eye on those, and some of them we have a little bit of a participation in order to understand what they are proposing and how can we use those recommendations in our Canadian framework kind of thing, right? So UL, there's a ULC that is enforceable here in Canada, but ULC usually they are developed after you have the UL in place. And the AC 509, they are working with, but Stefan and I, we are part of that development as well. They are working on publishing a new document in the next little while. And the lead for that is the lead engineer for ICON, which is one of the important players that we have in this industry right now, right? So another thing to have those leaders developing those standards is a very good sign for the industry in general, right? So, okay, so moving a little bit away, so just going back on that that slide that I show the framework here. So basically, it's very clear why we're putting a lot of effort on the ASTM side of things, because we are dealing with testing, standard tests for this particular time. And those standard tests are going to inform the development of design tests, design standards, and national building codes and everything, right? It's important to mention that in the US, they have a big effort going on the ACI side of things as well. I'm not going to spend too much time on that because I'm not part of that group, and also because ACIs are not enforceable in Canada. Of course, but we need to filter a little bit of our energy. But of course, this is going to be a huge achievement for the industry once ACI publishes the first standard tailored for additive construction in concrete and mortar, probably, right? And we're going to have ACI Toronto event in the next couple of days. And we are going to probably hear a lot about those updates, improvements, and deadlines and target dates for publishing those standards. And just going back a little bit and focusing a little bit more in the province that we are right now. So of course, we've done some work outside the province, but Ontario is where we are based off, and Ontario is responsible for 45% of Canada's GPD, right? So it's a very important province for the country. And again, most of the things that we have on the OBC, we're gonna have in the other standards, because some of them, they just follow whatever OBC is doing or whatever NBCC is doing, right? So in OBC, we have two categories of solutions, right? We have acceptable solutions and we have alternative solutions, right? What they see as acceptable solution, everything that is being already very, very much explored. Like, for example, concrete, structural concrete, steel, wood frame, steel frame, light gauge steel, all of those very popular ways to build, they are covered by the acceptable solutions, right? So whatever doesn't fit in acceptable solution, we can go the pathway of alternative solution, right? So, and it's funny because alternative solution section in the OBC, it's a very simple section, right? Which gives a lot of decision power to the CBO, right? The chief building official, which is part of the municipality most of the time. So basically, when it comes to alternative solutions, the CBO is going to tell you whatever they want to see in terms of research, results, tests, performance, and this and that, in order to give you a building permit for alternative solution, right? So as you can see here, this is pretty much everything that we have in the code regarding alternative solutions, right? So this introduction, which is a little bit long introduction, right? But this introduction is especially to show you guys that everything comes down to testing, right? So developing the standards, in order to develop the design standards, we need to develop the test standards. In order to develop the test standards, we need to do test after test after test. And before we get the chance to have all these standards published, everything available, and everyone is going to be able to print their houses and to use additive construction as a solution for their houses, until we get to that point, we're going to need to go through a kind of alternative solution situation, right? So one of the presenters here also mentioned design by testing, which is not exactly what we have in alternative solution, but can be something similar to that. We don't have design by testing here in Canada exactly the same way they have in Europe, and potentially probably the same way you guys have in India, but alternative solution is something closer to that, right? So that's the reason we decided as a company to put a lot of effort on testing, right? So we develop we develop a lot of research agreements with academia here, including Vahid, including Dr. Das, including Dr. Butler at York University, and other professors that we are still in talks in order to get some testing done. So we understood as a company, Printera, in order to get our business up and running in a global in a larger scale, we need to do a lot of testing. We need to do a lot of research. This is not actually something that we do just because we like. Of course, I came from academia. I've done my PhD with Dr. Das, so I like to do research very much. But it like as a business, it's not something that we necessarily like to do, because there's a lot of money involved. There's a lot of contribution involved. But at the same time, it is what it is. It's the stage that we are in the industry. We need to provide a lot of test results in order to develop all those documentations, right? So in terms of thermal requirements, for example, we have those 4 zones here in Canada, and we have different requirements in terms of R values, right? As you can see, we are located in a region that is potentially zone B or eventually a zone A, depending on the interpretation. And we are kind of not in a very good, in a very bad problematic situation when it comes to insulation and thermal performance. But of course, we are still in Canada. There's a lot of snow here. We had a couple of weeks ago, we had -22. So we of course need to be prepared for a very important thermal performance evaluation, right? So the good thing, I think that responds to some of the questions that you guys made to Dr. Das in terms of insulation. I hope I can kind of contribute to that answer here. But
Marcus,
basically,
sorry, I'm interrupting you. You have 2 to 3 minutes left.
Okay. Sorry about that. Yeah. So in terms of thermal performance, so we have the opportunity to change the insulation cavity quite easily, because we are basing our designs out of a computer model, right? So like increasing the size of the insulation cavity is not as hard when you're doing that with stud construction, right? So some cases you're going to need to increase the size of your stud. Some cases you're going to need to have double studs, which is going to just carry more cost to your solution, right? So this is one of the advantages that we have. I'm not going to talk too much about the research. This is a research that Dr. Das just published this paper about building envelope investigation. They are investigating thermal and water penetration. He already mentioned. I don't have anything in terms of results here, just to show you guys the research that we are doing in order to write those standards. So those results are being used for the standards that we are developing. This is part of the research that I was a little bit more involved in. Then we tested those walls under compression. We compared against the TMS, the Masonry Standard, which is a standard for the US. And we got like one of the walls, we got 94 times the minimum threshold to consider a wall a load-bearing wall, according to the TMS. And we did some testing with the prismas. That's the one that I mentioned that we are publishing the standard. We are on the final stage of the standard development, meaning that we are going over voting and balloting the next little while. As you can see, we did some testing. We got some results. We did some investigation in terms of material as well. We did a bunch of different directions. Same thing that the most of people are doing, as other than the oblique shear that is not as common. We did the oblique shear. We got good results out of the oblique shear, and we are recommending that as part of the standard development as well when you need to evaluate the material shear performance, not the specimen, of course, not the large scale. We've done some simulation. We were doing some numerical investigation. This is part of the work that we are doing with Vahid as well. This is an independent from what they are doing. We did some simulation on our side. Vahid and his students, they are doing some simulation on their side. And we are using, of course, some of the results that we achieved on the smaller scale to develop the interlayer bond behavior for our modeling. We did some modeling. We are about to test those specimens. I'm going to let Vahid to talk more about the testing that we're going to be doing the next little while. And just to finish here, to conclude, basically, we came up with a testing framework that we are doing for fresh properties, hardened properties, and also for the wall assemblies for certification purpose and also for alternative solutions purpose. Of course, the wall assembly testing framework is the most important one. They want to see large scale components behaving, the behavior of them. In terms of allowing us to build more and more structures, right? So a few other standards here. Unfortunately, I won't have time to talk more about the other things, but we're doing a lot of policy advocacy as well. We are doing we were doing some talks with the parliament. We went to the parliament a couple of months ago to talk about the importance of development of standard development and the need that we have in terms of funding. We've been talking to the NRC as well. I see some folks from NRC here trying to get some more support, trying to get some more funds specifically for the development of standards and have this industry reaching the mainstream. Thank you so much. Thanks for having me. I'm happy to answer any questions you may have. Thanks, Vahid.
Thank you very much, Marcus. It's great to see that there are efforts on developing standard codes. So we have the pleasure to working with Printera for the last year, and they're really heavily involved in research aspect of the things. They're very up to date. So I don't know if we have any questions in the chat box. I still don't see any question. But Marcus, so I will ask a question. So we have a question. Let's just go to the audience, and then I will ask my question later.
Okay.
Any codes or regulations for thermal performance in terms of the lattice cavity design, thermal testing of the wall and the material? In specific, I want to know the thermal conductivity of the material you're using.
So I don't have any results to share here right now, but the paper that I showed, Dr. Das just published a couple of weeks ago, I think a couple of days, is just a very fresh one. They published, and Dr. Das mentioned some R value thermal conductivity results out of that, right? So the standards that we were using, and Dr. Das can speak to that as well, were just basically existing ASTMs for masonry construction when it comes to thermal evaluation, right? So we were using the same exact standards. At some point, we were going to be providing probably some guidelines in order to use those existing standards for specifically for additive construction. But at this time, we didn't see the need to develop a dedicated standard for thermal evaluation of additive construction components, right? So we're just using the existing ASTMs for that.
Okay, thank you. So, Marcus, I know that you're heavily involved in these code committees. Can you talk about what is the where do you see these codes in, let's say, 5 years in the near future? Do you think we'll be at the point that we have a very reliable code that covers most aspects of the material and structural design?
Yeah, so that's our wish, 100% for sure, right? So we've been talking to CSA as well. They were part of, you were there, right? So at the NRC meeting in January, they were there, and we were expecting to have them a little bit more engaged on those standard development, right? So especially because CSA, they require a fee to start a committee, right? Which is different from ASTM, the ASTM committees, right? That we can establish the committees and do the work and use their platform without paying any fee. Of course, we're going to be contributing with our work, but CSA is a little bit different, right? They want us to write the standards, and they want us to pay for for us to write the standards, which is a little bit tricky. We wish that we have, and that's part of our policy advocacy. We want to be speaking and talking about this problem, because we need, in order to achieve the mainstream, we need to have those folks more involved in it. And so we need to have the NRC a little bit more involved. We know that they are putting a lot of effort in terms of like creating guidelines and studies, but we need, as industry partner, we need to see them very much engaged in the development of those. But in 5 years, it's totally doable for us to get to the point, especially because we're developing all those ASTMs already. It's totally doable for us to get one ASTM that covers additive construction in general. Referring back to those ASTMs is totally doable, and I hope we can get to that point in 5 years from now.
Okay, thank you. So we have time for one last question. Is the ISO standard applicable for use for structural elements? And then do the standards provisions stay in place formwork? So I don't know what exactly the second part.
So ISO, it's most of the time it's not enforceable here in Canada unless we have a CSA or a building code that is referring back to a ISO, right? So the good thing that ISO is an international institution and ASTM is also an international institution. ISO most of the time is more focused on European market, and they have a better framework to meet the standards for European market. And ASTM is more focused on the Americas, right? So South America, North America, and Central America in general, right? So that's the reason in Canada we are part of ASTM. So when it comes to international standards, it's really tricky because you gotta have a local standard that refers back to that international standard in order to use that. So it's possible, but it's not often used as a practice, right? So we are more leaning towards ASTM. So when it comes to ASTM and ISO, most of the time they are more focused on testing materials, right? So the cylinder test that we know very much, like we know very well as an industry, the cylinder test, all the testing that we have in terms of concrete is most of the time based on ASTMs, right? So it's going to be hard. I never had the chance to develop a design that was based on an ASTM guideline. I don't know if they have some guidelines like this. We had a similar discussion in the committee a couple of days ago in the committee meeting that we had like last week, that someone was asking, like, can we have an ASTM that we can develop the design guidelines? It's not that common, right? I think like you can, but I don't know how much enforceable that's going to be, right? So that's the reason we use ASTM and ISOs more for nomenclature, the way you like standard practice for basic stuff, and also testing. And when it comes to design requirements here in Canada, we go more for CSA, the same way that the Americans, they go for ACI.
Okay, thank you very much again, Marcus, for this presentation. So we will move on to our next presenter, but before that, I'm going to hand in the moderator role to Dr. Biranchi Panda from IIT Guwahati. So Biranchi, please take over, and
Sure,
we'll have a presentation in a few minutes. Thank you.
So yeah, thank you, Vai. So we'll move to our next presentation by Dr. Rahul. So Dr. Rahul is an assistant professor in the civil engineering department, IIT Tirupati. So previously he was working in the Ghent University. His research focuses on concrete 3D printing, rheology of cementitious materials, and some modeling of cement-based materials. So with this brief note, I would like to invite Dr. Rahul for his presentation. Dr.
Yeah,
Rahul, the stage is
yeah,
yours.
yeah. I think my video has some issue. It's not switching on.
No issue. Yeah, please share the screen.
Yes. Hi. I'll just share my screen. Uh,
Yeah, we are unable to see it now.
yeah, you can see my screen.
Yeah, it's loading now. Yeah. Yeah, that works.
Yeah. Hello. Thank you, Balaji, for the introduction. And hi, and good evening or good morning, depending on which part of the world you are. So I'll be speaking on this topic, plastic shrinkage cracking in 3D printed concrete elements. So I'll specifically talk about why this is a concern in 3D printed concrete. And since this is a concern, how do you measure plastic shrinkage issues in 3D printed in 3D printed concrete? Now, if you have to mitigate this problem in field or when you're doing 3D printing in the lab, like a precast element, so what are the strategies that you can adopt? So this will be the outline of my presentation. I'll introduce to the terminologies in plastic shrinkage. Then I'll go into some of the methods that can be used for early age plastic shrinkage. This requires a special discussion because when you say shrinkage measurement in hardened concrete, you can just physically take the specimen and put to LVDTs or put to strain gauges and measure shrinkage or measure the changes that's occurring with respect to time. But early age concrete, it's not something you can physically hold. So you might require a specialized experimental setup. So this is something that we'll talk about in this section. And then after that, we'll talk about how to mitigate early age shrinkage cracking in printed concrete. What are the strategies we can adopt? And then we'll summarize the talk. So to start with the introduction, so this is something you would have probably already heard quite a lot. What is 3D printing? So it's basically a special concrete that's printed through a nose, that's extruded through a nozzle based on a virtual model. Based on what the virtual model tells, the printer will move to make the specialized shape that you want. When you compare it with conventional casting, it has two major advantages. One, it doesn't need formwork and it doesn't need compaction. It looks very simple when you say it doesn't need formwork and compaction, but that's something that significantly constrains traditional casting. Because when you say you need formwork, you are restricted with the kind of shapes that you can produce with conventional casting. When you say you need compaction, you can't make thin elements because you have to worry whether you can reach your needle vibrator through these thin elements, and these issues come into picture. So you can forget about these two things when you do 3D printing. And this means that you'll get significantly enhanced architectural freedom because you don't have to worry about formwork and compaction issues, and that means you can make any shape that you want. The other three advantages that I've listed here, that's less labor, less production cost, or reducing time. This is expected with any additive manufacturing process because you're automating the process. These are added advantages coming from that. So coming into the main focus of this talk, that is shrinkage. Shrinkage basically occurs due to either an internal or external moisture loss. External moisture loss is driven from the driving factor is evaporation. Internal moisture loss is occurring due to continuous hydration occurring in the system, which is using up the moisture that's inside the concrete and reducing its RH, relative humidity. So what problems happen due to plastic shrinkage? This is a slab, not 3D printed concrete, a conventional slab. Just after a few hours, you can see these cracks appear on the surface. So just by looking at it, these cracks majorly are aesthetic issues, you can say, because it's mostly surface cracks. But in terms of the long-term performance of the structural element, you can end up with problems because mostly you're going to create these cracks on the surface. And that means it's your cover concrete that's getting affected. So the quality of the cover concrete goes down, and this means that there's more easier ingress of harmful ingredients like chlorides or water that can go through the cover concrete and reach your steel, where you can have problems like corrosion or other durability issues sometimes. Sometimes if the cracks are large enough that you had very severe plastic shrinkage cracking, you may even have a structural integrity issue also from shrinkage cracking. So this is the issues that can arise from plastic shrinkage. And now, why is this so much of concern in 3D printed concrete? Now, one thing, as I was saying in the beginning, is what drives plastic shrinkage. That's basically evaporation. So because evaporation is a driving factor, it would depend on how much of the concrete is exposed to the external environment, particularly during the early stages. If you see, when you say early stages, if you look at 3D printed concrete, you can see the entire concrete is exposed just from the point that the concrete is deposited. If you see the first slide here, because the entire concrete is exposed just from the point it's deposited, unlike a traditional concrete, let's say you're making a column or a wall, where it would remain protected in a formwork. That's for 24 hours, because that's the limit that Indian standards put for removing vertical formwork. That's not the case here. The concrete is exposed to drying immediately. So there's evaporation starting right from the point the concrete is deposited. This is one problem. And since you've probably looked at mixed design of 3D printed concrete in earlier lectures, you would probably know by now that binder content is very high in 3D printed concrete. And the binder is the one that's undergoing the shrinkage. More binder, there's more susceptibility to shrinkage. And the last point, if you see, is this large surface area to volume ratio. And this comes from the fact that mostly 3D printed concrete are slender elements. You can again go back to this example. These are very slender elements. But slender elements is characterized by high surface area to volume ratio. That means you are likely to face more shrinkage cracking in these elements as compared to other types of elements where it's not non elements that are not as slender as these ones. And the other factor that may influence or that may again aggravate shrinkage is the type of ingredients you add also. A lot of 3D printed concretes, for instance, use silica fume. And silica fume in traditional concrete is known to cause plastic shrinkage cracking. And this here silica fume probably is added to meet your rheological requirements, in have no thixotropy or have rapid stiffening and structural buildup in the system. These are advantages that silica fume can provide. The problem with those ingredients could be that you may end up with huge susceptibility to plastic shrinkage cracking. You can see this in this printed element taken from this literature here, how severe the plastic shrinkage cracking is. And the layers of the concrete also, the layering effect, that the layers of 3D printed concrete, they may also get influenced. If you see the crack pattern, some places you can see the crack takes a more easier route through the interlayer since it's already weak. So more and more plastic shrinkage means because of the crack propagation through the interlayer or the shrinkage of individual elements in the system not behaving monolithically, this can result in debonding as well. So there are studies that indicates this increased bond strength loss with time, which could be due to plastic shrinkage. Yeah, so one of the other aspect also I wanted to mention is how plastic shrinkage may also influence the microstructure of hydraulic cementitious systems. This is, you can see in this literature here. Two samples were studied, one with one which was subjected to drying, and another which was not subjected to drying. And you can they have measured porosity and the amount of hydrates that's formed in the system in a small layer that's close to the aggregate. You can see throughout for the dried concrete, there's more porosity and there's less amount of hydrate that's formed. It's because of the early removal of water from the system. This has resulted in less hydration occurring in these areas, and that's resulted in a greater porosity, particularly in the ITC regions of the concrete. So this is very less literature on this, that the microstructure of the concrete that's subjected to early age drying could differ from a concrete that was where this early age drying was not occurring. So coming into one of the main aspects we'll cover in this section, that's how to assess plastic shrinkage. So when we wanted to work on plastic shrinkage, plastic shrinkage in 3D printed concrete, one of the first things we want to see was what are the different ways in which we can measure it, and what are the ways that's available in the literature currently, and can we classify it, and can we try to identify which of these techniques in general would apply to 3D printed concrete. So in this regard, we had classified it into a contact-based 3D print, contact-based shrinkage measurement approach. Is a non-contact based. So contact-based is basically where you put an embedded sensor and then take measurements using the embedded sensor, or the traditional way, you put a strain gauge or an LVDT and then make the measurement. Non-contact is you send a laser and see how much deformation is occurring, or you use techniques like you take digital images and then you use digital image correlation techniques to see how much of displacement is occurring on the surface on contact based. So if you look at contact based approaches, particularly from viewpoint of shrinkage, this is one type that you've been we generally used as FBG, fiber Bragg grating, which is based on varying refractive index. And the other common approach is software sensors, which is very common in health monitoring studies. If you look at the problem with embedded sensor is, one, there's a high chance that the embedded uh, sensor may undergo slippage. So as the matrix around it shrinks, the entire strain may not get transferred to it if there's slippage occurring at the system. As the material hardens, there's a possibility that can even deform, and then this may also result in incorrect shrinkage measurements. And this is again okay if you are casting the concrete in a mold, but for printed concrete, embedding sensor is a challenge. How do you embed the sensor? This is again something that we may have to look at if you're looking at sensor-based approaches for shrinkage measurements. But the advantage sensors can provide is, if you embed it, you can take the early age measurements and then use that same sensor for long-term health monitoring. So let's say certain durability issues has been triggered, and if that is causing some expansion in the concrete after several years, it can be measured, particularly if you're using software sensors, because it can remain intact for a very large number of, much more number of years as compared to some of the other sensors. The other contact-based approach is using specialized molds, and you use specialized setups to make shrinkage measurements. You can see here, the concrete is cast in this, and then you use a movable end here where an LVDT is attached, which would continuously measure the change occurring in the system. The most common, some of you could be familiar with, is your corrugated tube test. You place the material, and this is only for autogeneous shrinkage, not for it only captures the early age shrinkage arising from internal moisture loss. But again, you need a specialized mold for the setup. Here as well, you need a specialized mold, and you need to have a setup where you can attach an LVDT, make shrinkage measurements through that LVDT. These aspects are again, very tricky with 3D printed concrete. Embedding in a mold or even having specialized LVDTs attached to it, it becomes a hazard. When you come to contact-based measurements, one set of studies, if you look at, they look at using laser sensors. But again, many of these laser sensors rely on having specialized mold. This is very common for very probable mortars. This is called a shrinkage cone. You have the cementitious mortar placed in this, and a cone is placed on the top. And then a laser is used to make continuous measurements depending on how much shrinkage is occurring in this conical portion. You can make an assessment of how susceptible the material is to shrinkage. Thin laser shrinkage setup, this is another option. So you have thin layer made, and then two reflectors are placed on top of it. And then along with the reflector, you have the sensor, you have detectors also, which will send lasers and then detect. And depending on how much these reflectors translate based on how the shrinkage occurs in the system, you can probably compute shrinkage rate. So as shrinkage occurs, this will move inwards, this will also move inwards, and that can be computed by using these laser displacement sensors. But again, placing these large reflectors could be a challenge. You need to get good data. The reflector has to be large enough, and then placing it on top of the surface could be somewhat challenging. The other non-contact based is digital image based. In digital image based, you create a grayscale pattern with high contrast, a pattern that has high grayscale contrast, and then you capture that images at different intervals of time. And then based on how the grayscale, the pattern that you see is varying, you use a cross correlation function to see how much to what extent the pattern is varying. From that, you can make displacement field calculations. So one advantage you get is, if you have the speckle pattern made throughout the surface, you get full field displacement data, unlike point displacement data, point-wise data you get with LVDT. The entire field you can get the full displacement data. But then when you do this full field displacement data with fresh concrete, one of the challenges we face is, what is the paint you can use on a fresh concrete? Because certain paints from some of the earlier studies we did seems to interact and sometimes even delay cement hydration. Especially in the top layer of the concrete. And the other is, the paint shouldn't seep through the concrete also. It should remain on the surface. So this is one challenge that we face using which, in general, there are chalk-based paints as well as polymer-based. So which one to choose is one of the things we have to figure out when we use DIC systems. So in general, when you look at shrinkage measurement methods, you have sensor-based approaches, which involves contact with the specimen, or using LVDTs, which again involves contact with the specimen. Or you can have methods where you don't contact the specimens, like the laser displacement and DIC. Obviously, I think by now you would realize that non-contact is what would possibly work for 3D printed concrete elements, because having specialized mold or physically touching and taking readings is very impractical with fresh concrete. So for printed concrete, mostly what we find suitable is DIC-based test setups, or laser displacement-based test setups. So this is one of the test setups we have in our lab, which was developed in our lab. So here, instead of doing a full field displacement, we are putting 2 pins, and then using a correlation, using a MATLAB algorithm to track the motion of the spin. So because plastic shrinkage depends on so many factors, including wind velocity, these aspects are kept controlled. DIC depends on how well lighted your specimen is. So we have a white light source here, which lights up the specimen, and the camera is used to continuously take images of the specimen. You can see the pin that's captured here, and then the edge in the pin, the motion of where we have a grayscale contrast, and that is continuously tracked using an edge detection algorithm in MATLAB. This allows us to make these continuously monitor the change that's occurring in these 2 pins, and that can be processed to obtain the free shrinkage data. You can see how the resolution that we're getting here. With even very not so expensive digital cameras, you can get very good data if you are using a good edge detection algorithm, which is mostly from the processing side. You can get very smooth shrinkage deformation data you can see here. And also another thing you see here is these are 3 trials run on the same system. You can see how reproducible the data is. So repeatability wise, reproducibility wise, and the simplicity as well, because the experimental setup is as such is not so complicated. You just take a camera and take images of the specimen. Processing, there is some some skill required in the processing side, but if you have that, this is a very simple technique which can monitor free shrinkage in printed concrete system. So here again you can see what we have captured from the free shrinkage data through DIC. When you see shrinkage data, you can see here within 360 minutes, the level of shrinkage strain that's reached is one aspect. So for certain types of 3D printed concrete, for example, SF is a mix that contains silica film. Shrinkage strain is as high as 10,000 micrometer per meter. That's very high shrinkage strain. Even these values are very high compared to what you would expect in traditional concrete. And this is the point I was making earlier, because of the high binder content, the free shrinkage can be extremely high in these type of systems. And the other aspect is the trend that you observe in the shrinkage measurement. Initially, you see very rapid increase, which is called the constant rate drying in porous media when you study drying in porous media. And then after that, you see where the shrinkage rate of increase is falling, which is called the falling rate period. In this stage 1, this is mostly driven by the evaporation, direct evaporation, where there's continuous water channel from the interior to the exterior. So there's a continuous water channel from interior to exterior. So moisture transports from interior to exterior as evaporation occurs from the exterior. Stage 2 is when the channels are not continuous anymore. The channels are starting to become discontinuous, and there's air entry in the system, and there's direct evaporation occurring from within the pore, and that really slows up your increase in shrinkage strain, as you can see here. This is where a lot of water gets removed from the system, and there's a rapid increase in shrinkage. And then after that, it falls down as air entry occurs, and the water channel becomes discontinuous. One aspect I thought I'll mention in the measurement part is a lot of studies do not focus on how viscoelastic parameters can influence shrinkage. So if you look at shrinkage cracking potential, there is shrinkage strain that's being built up in the system, which results in tensile stresses. A lot of these tensile stresses may get relaxed because of the highly viscoelastic nature of the early age concrete. So here in this example, if you see here, certain mixes, if you see here, for example, the one that's indicated by this blue line, this is having a very high storage modulus. Whereas if you see here, on the right side image, which measures loss modulus, certain mixes are very high loss modulus. So again, just to give you a background on what these parameters could mean, this is determined from a small amplitude oscillatory shear experiment, SAOS, where you can get 2 parameters, 2 moduluses, which characterize viscoelasticity of the material. One is storage modulus and the other is loss modulus. Storage modulus is how solid and rigid the material is, and loss modulus is how viscous your material is. So more viscous means it will have more dissipating characteristics. So a lot of the stresses that gets built up, it can relieve it with respect to time. So it will probably exhibit a higher stress relaxation capability because of its higher dissipating capacity, as you can expect from the high loss modulus. Mixes which with high storage modulus may potentially appear more rigid and stiff and could crack much more sooner as compared to the other mixes. And this, when we look at shrinkage cracking studies, where we don't allow the specimen to expand, we restrain that free motion and see if the specimen is cracking, and at what time that specimen is cracking. We find that the mixes where there's a lot more relaxation occurring, where the loss modulus is high, the cracking is a lot more delayed as compared to the other specimens. So this is again pointing out to how these parameters could come into, when you look at how susceptible your concrete is to cracking. So because shrinkage strain could be very high, but the stress that's being built up from that strain, if that's relaxing substantially and very quickly with respect to time, then maybe your risk of shrinkage cracking is reduced. So this also points out to where how modeling approaches could be also brought in to study plastic shrinkage. Modeling approaches that can account for viscoelastic characteristics of the mix. Yeah, so going into mitigation strategies, when you look at shrinkage mitigation, there are all these traditional approaches like shrinkage reducing admixture, one very common thing that we do. So this is directly added in the mix at the time of casting. You have fibers that can be added in the mix. They increase the tensile strength and probably may not, because the tensile strength is higher, will not probably result in cracking. You can have internal curing type of materials like lightweight aggregates. If it's saturated, it supplies back moisture and increases the relative humidity inside. Particularly if you're worried about autogeneous shrinkage, same with superabsorbent polymer. Autogeneous shrinkage, particularly, you get substantial reduction when you use these materials. But now you have to think of these traditional methods, how it would work for 3D printed systems. Now, SRAs, if you look at the problem, one you may face with SRAs is it's quite expensive. Many SRAs like polyethylene glycol, it's already printed concrete is expensive with the huge amount, with the chemical admixture that's required to meet the rheological requirements and the high binder content. So on top of that, when you bring in other aspects that increases cost, I'm saying from an industry perspective, this may not be a very suitable option. Fibers are effective. It increases your early tensile strength, but the drawback would be that
Rahul, sorry to interrupt you. You have 2 minutes remaining.
yeah, fibers, the issue would be that it can influence the pumping characteristics. So we may need to look at some other alternatives, and lightweight aggregates and super absorbent. Also, these are some of the issues that you might. The cost is one of the issues, particularly with super absorbent polymer, and can also influence your strength, adversely influence your strength and porosity. So we sometimes look at one of the aspects we're studying is can we look at more cost-effective option, waste-derived materials, particularly bio-based materials that can have high swelling potential and can be potentially integrated in 3D printed concrete, where you can have a reduction in plastic shrinkage. So you can see an example of a material that we are studying here. It's a chitosan-based biopolymer, and you can clearly see there's a reduction in plastic shrinkage. Unlike the other materials like SAPs, commonly used SAPs with high, which also has high swelling potential, we don't see any influence on strength. Whereas if on the case of SAP, you will get this performance, but your strength and porosity would be adversely affected. But here, in the dosages that we are looking at, we don't see statistically this looks the same. We don't see a lot of difference. And another aspect that we can do is spraying on the concrete surface using membrane curing based agents. This is also quite effective. You can see stage 1 is substantially delayed, air entry is substantially delayed, and falling period also there's practically no further increase in shrinkage. So this is something else that can be also looked at. So these studies sort of indicate the kind of curing approaches that we may need to define, or when we make codal provisions for 3D printing. This what type of curing we adopt, and when you should start curing, as this can help substantially. As you can see, it's something 7,000, which has come down to like 2,500. So the kind of effect that it can produce. So to summarize this presentation, as I was pointing out earlier, 3D printed, and in the beginning of the presentation, shrinkage is a major concern for 3D printed concrete elements because no form large binder, high binder content. So first thing you have to look at is how do you measure the shrinkage? How do you assess shrinkage? So traditional approaches like LVDT strain gauge is not very suitable for fresh concrete. So non-contact methods like DIC is more suitable. They're fast, quite accurate, as you can see here, produce repeatable data. Various factors can influence, not just the strength evolution, viscoelasticity can play a role, as I indicated in one of my slides. Mitigation strategies, a lot of conventional approaches are existing in the literature, but when you see it in purview of 3D printing, it can cause pumping issues. High cost is the other concern. Already the mixed design is costly. So new methods like the use of biomaterials, which can have high swelling potentials, could be explored in future works. Yeah, thank you.
Yep. Thank you, Dr. Rahul, for the detailed presentation on the shrinkage. Okay. So we'll take some question from the chat box. There's one question. How the shrinkage is linked with the scale of 3D printed concrete? So I guess
Yeah,
what you mean by, yeah, I think the scale, like if you print a small scale sample and if you print a large wall, how the shrinkage differs?
yes. So, like I said, the problem here is there are two aspects when you say scale, actually. One is what we have in the sample that we studied. What is the exposed surface area to volume ratio there, as compared to the exposed surface area to volume ratio in the actual sample. So this is one parameter that we may have to account for. So which may differ. So the laboratory measurement may differ from your what you're actually seeing in the field because of this. Uh, yeah, this is one aspect which you have to see, and the other is if you have in the actual sample, if there's curved surfaces that's existing, these curved surfaces create more restraint to shrinkage, and there is a possibility that you can see cracking in these areas. Uh, it's correct. So it's difficult to exactly replicate that shape here, uh, since we can't do these complex shapes in laboratory experiments. So we can only measure using simple laboratory scale, like prism based elements, and probably we may have to use some modeling approaches to see what if the shape differs and how it would impact shrinkage.
Okay, that's good. Yeah. So,
Yeah.
Dr. Rahul, I have one question from my side. So, let's say, like sometimes this 3D printed of concrete, it's being used as scheme. So, we print the formwork and put other materials inside that. So, in such examples, so what is your comment on this kind of like applications where we print the skin or let's say the formwork and then we pour a secondary material inside that? So, how do you see shrinkage in that examples?
No, I couldn't hear you. Can you just repeat your question once again?
Yeah, I was trying to say that there are some application of 3D printed concrete where we print the formwork, okay,
Yeah.
and then we put the secondary material in that. So in that
Correct.
case, the inside concrete it is secured from outside. So
No. So here there are two elements actually. The inside concrete is a traditional concrete, and
yes,
instead of just using a wooden formwork or a instead of using a wooden or a steel formwork, you're using a concrete formwork.
Hmm.
So the formwork is still concrete, and that can undergo shrinkage, right? And that can crack. One thing. Second thing is this is something that I've seen in some of my colleagues study earlier, the place I was earlier. So when you have the new concrete added, particularly added within a 5-6 hour duration, there's the possibility of moisture transport from the 3D printed moisture transport between the 3D printed concrete and the mold cast concrete which you're pouring
right.
inside. So this can also create problems. This moisture transport may also induce shrinkage in some of these systems, particularly you may say debonding occurring between the new infill and the outer concrete.
Okay, correct. Yeah.
Yeah.
So yeah, I think there is no more question. So yeah, sorry, there is one more question. I think I'm missing it. Wait, sorry. So he's asking something regarding the admixtures. So
So there
whether
are a few
restraint
questions.
shrinkage is similar for 3D printed concrete like conventional concrete.
Yeah, so when you study restraint shrinkage, the idea is to restrain the free shrinkage. And because your shrinkage is restrained, it will crack. And we see the time of cracking, how big the crack is, whether it propagates rapidly. So traditional methods is you cast in a slab and then see the cracking on a slab. This is one option. But in 3D printed concrete, this is difficult. So what I've seen from literature is they make wall elements and then they put rebars, small rods into it to create restraint. Then
Mm-hmm.
you see how the cracks are formed in the wall element.
Right.
So you may need to adapt from the traditional restorative gauge test you have to suit
Oh.
3D printed concrete.
Mhm. So yeah, there is one more question. What is the efficacy level of PEG on reducing shrinkage? Does it affect the
Yeah, PG,
strength?
you mean Yeah, PEG is polyethylene glycol, right?
Yeah.
That's right. Yeah.
So he's asking what is the efficacy level of PEG on reducing the shrinkage? Does it affect the strength? And in that case, what is the molecular weight role?
Yeah, PEG basically works by lowering the surface tension of pore solution. So when water leaves, because the surface tension is reduced, the level of capillary pressure buildup gets reduced. Yes, molecular weight will play a role because that would impact its surface tension characteristics, and therefore it should influence your properties. But PEG at very high dosage has been known to cause strength reduction. It causes reduction in strength and increase in porosity. So yeah, at higher dosage it's a problem, but it's effective. We have studied PEG with in 3D printed concrete, and it's effective in reducing shrinkage. But higher dosages will cause other issues.
Okay. Yeah, we'll take the last question. So how the lightweight aggregates can help in mitigating the shrinkage, and what is the possible limit in this case?
Yeah, so generally the lightweight aggregates that we use for shrinkage mitigations are coarse aggregate. And coarse aggregate, most 3D printed concretes are not with coarse aggregate to begin with. Second, it works if your coarse aggregate is saturated. Yeah, you will get some strength reduction. Yes, but how to introduce the coarse aggregate in concrete to the levels? Because normal concrete you can have quite high levels of coarse aggregate. Here, even if you have coarse aggregate, it will be quite low. So at that low dosages, will it cause significant impact, significant amount of internal curing that we have to see. And the other issue is when you increase it, when you have high levels of lightweight aggregates, they are more porous and your strength will come down. This is the other issue you may have to tackle.
Okay. Yeah. Thank you very much for answering all the
Finally,
queries.
my camera started working. I'm sorry that it didn't work earlier.
Yeah. Good
Yeah.
to see you. So yeah,
Yeah.
thank you for answering all the queries.
Thank you.
So thanks.
Thank you for inviting
So
me.
we'll
Yeah.
Yeah. So we'll move to the next presentation.
Thank you.
Thank you very much.
Yeah. I'll
The
stop
next
sharing.
presentation is by Professor Bahid. So like he's the one of the PI in this project with me. So Professor Bahid is an associate professor in Carleton University, Canada. So he specialized in design and performance of structure, reinforced concrete. So he has expertise on hybrid simulation with finite element modeling. So without taking much time, I would like to invite him to listen some core important work of the project from him. So Dr. Bahid, I think the floor is yours now.
Thank you very much, Biranchi. So I'm sharing my screen. If you can just let me know if you can see the screen, and I'm switching to the full screen mode.
Yes, visible.
Okay, perfect. So hello, everyone, again. So I am going to talk about a holistic approach to understanding and optimizing behavior of 3D printed concrete. This is a project that basically my student, Murtaza Mohemi, is working on over the last 2 years at Carleton University. And we have been working on this project in collaboration with the IIT Madras and IIT Guwahati. So if I can just remove this, okay. And our industry partners are Printera in Canada and Tivesta in India. The project is sponsored by IC Impacts and the Ministry of Science and Technology in India. We truly, when we started this project, we truly followed a holistic approach. We looked at the behavior of 3D PC from different perspectives, from material level, architectural level, and structural level. And in each of these aspects, we had some objectives. At the material level, we are working at Carleton to fully understand the mechanical response of 3D PC under various loading conditions. Our Indian partners, Dr. Panda and Santanam, are working on the development of new mix designs to reduce carbon emissions by using alternative binders and higher aggregate contents. At the structural level, our efforts are towards conducting numerical studies and experimental work to evaluate the safety of 3D PC buildings under lateral loading, for example, wind and earthquake, and also to develop effective reinforcing methods. One of our collaborators, Dr. Cheryl Boyle from our architectural school, is working on topology optimization of 3D PC building. And basically, all these aspects are connected to each other and will help us to make more meaningful advancements in this area. So in today's presentation, I'm going to just give you a short glimpse of some of these projects that we are working on in Carleton. I'm starting with the material level of study that we are doing. And we have conducted a comprehensive experimental work to evaluate the full mechanical response of 3D PC under various loading conditions. Now, the reason that we pursued this project was that if you look at the literature, there has been significant efforts done on measuring mechanical properties of 3D printing concrete. They focus on various aspects, printing, effective printing parameters, effects of porosity, effective addition of fibers, and the behavior at the interlayer. The one limitation of existing studies is that their main focus was on measuring the strength and not the complete stress strain response of the material. And it is very important to know the complete stress strain responsive material because that basically helps us to understand the elastic modulus, the ductility of the material, which is important for earthquake analysis, the fracture energy and energy absorption of the material. And in general, if you want to model 3D printed concrete structures in computer software, we need to define their stress strain response. So this has basically motivated us to work on this aspect of the project and basically look for or investigate the stress strain response of 3D PC under various loading conditions. So in our experimental work, we basically defined 6 different mixtures. Here we see the properties of each mixture. The main parameters that varied between these mixtures were water to cement ratio, which varied from 22% to 41%, the cement to sand ratio, which varied from 40% to 109%, and the presence of fibers. So the first 4 mixtures did not have any fiber content, and the last 2 mixtures had 0.3% and 1.2% synthetic fibers. The printer that we used to print our specimens it was a small-scale 3D SCARA printer with a nozzle diameter of 15 millimeter and printing speed of 1 centimeter per second. After printing the specimens, we conducted 4 types of tests: the uniaxial compression test, 3-point bending test, double shear test, and tensile splitting test. In the uniaxial compression test, you can see that we use cylinders. And the direction of the layers is perpendicular to the direction of the load. In the other 3 tests, the direction of the layers are parallel to the direction of the load. And we position the specimen such that we have an interface between the 2 layers right below the loading load. And this enabled us to measure the tensile strength, response and shear response at the interlayer, which is basically what we are mostly interested in in order to be able to calibrate our structural level models. So one important aspect in our test was the displacement and strain measurements methods that we use. So we investigated 3 different methods: digital image correlation system, which here you see the setup that we use, strain gauges, and readings from the loading machine. And what we realize is that there is a significant difference between the measurements from DIC and the strain gauges versus the measurements from the loading machine. And if you consider the brittle nature of the material and the small level of the strain, so you can see that we are dealing with significantly small strains, it is very important to use precise measurement techniques in order to characterize the stress strain response of 3D PC. So if you look at the literature, there are some studies that report the stress strain response, but they're mostly rely on the machine readings and the loading, the JAX readings, and those results can be questionable. So throughout this experimental program, we use a DIC for the displacement and strain measurements of our specimens. So let's look at a couple of the results. So here are the results for the uniaxial compression test. Each graph represents a compressive strength versus a axial strain. Each graph is for particular cement to sand ratio. So C/S is the cement to sand ratio, and it varies from 40% to 109%. The black lines represents the results of the mold cast specimens, and the red ones represents the results of 3D printed specimens. We repeated each test 3 times to investigate the variability in the response. So one thing we realized is that at relatively low C/S ratios, the stress strain response is relatively nonlinear. But as we move to higher C/S ratios, the response becomes more linear. And also, obviously, as we increase the cement content, the strength, the compressive strength of material increases. But the increase in compressive strength is more significant in mold cast specimens compared to 3D printed specimens. If you look at the bar graph on the bottom right corner, you can see that the first few bars represents the compressive strength of mold cast specimens. And as we increase the C/S ratio, cement to sand ratio, the compressive strength consistently increases. But if you look at the 3D printed samples, we don't see that consistent increase in the compressive strength. And the reason is that the damage in the 3D printed specimen happens at the interlayer and not just the concrete matrix itself. And I will elaborate more on that in the next slide. The next interesting fact here is the variability in the response. So we observed that we have higher variability in the 3D printed responses compared to mold cast specimens, which again shows the sensitivity of the specimens to the printing condition and printing process. The variability in the response increases as we go to higher C/S ratios. Addition of fibers also help to increase the compressive strength of the material and also reduce the variability in the mold cast specimens. So looking at the failure mode of the mold cast specimen versus the 3D printed specimen under uniaxial compression loading, if you look at the mold cast specimen here, you see the strain distribution in the X direction from the DIC measurements. So we have a typical crushing failure in a concrete cylinder. We have these vertical cracks that are more or less uniformly distributed along the width of the specimen. These vertical cracks indicate lateral expansion due to Poisson's effect, as well as crushing in the concrete. And you can see that we basically use the full capacity of the material. Basically, all these cracks are uniformly distributed along the width, which shows that the failure actually happens due to the failure of the entire cylinder and not a localized failure. If you look at these strains in the other direction, there is no meaningful pattern, which is what we expect because you're applying the load in this direction, and the majority of the strain happens due to the expansion. If you look at the results of 3D printing, you see a very different strain distribution. So in the both X and Y directions, we have these concentrated zones of strain that are in the horizontal direction and align with the locations of the layers. And these strain concentrations shows that we have damage in the interlayers, basically at the interface between the layers. And that damage basically prevents the concrete matrix itself to reach its full compression capacity. And that's why when we look at the compressive strength versus strain response for 3D printed samples, it's relatively lower than mold cast samples. So that's one of the contributing factors. Moving on to the double shear test results. Again, each graph represents a particular C/S ratio. So the vertical axis is the shear strength of the sample, and the horizontal axis is the shear slip. We see a similar trend to the compression test results that by increasing the C/S ratio, the shear capacity of the specimen increases. But again, this increase is more significant in the mold cast specimens compared to 3D printed specimens. And again, the reason is that the shear failure, we position the specimen such that the shear failure happens at the interlayer, and the interlayer is weaker compared to the concrete itself. And changing the concrete mixture does not have as significant of an effect on the properties of the interlayer as it has on the property of the concrete itself. So by changing the mixture, increasing C/S ratio, you see more effect on the concrete matrix than on the interlayer, and that's why we see a higher increase in the mold cast specimen, the shear strength of mold cast specimens as we increase the C/S ratio. Another interesting fact here is that if you look at the response of mold cast specimens, once the shear cracks happens in the specimen, we have relatively gradual change in the stiffness as the crack propagates. But in the 3D printed sample, all the results are very brittle. And as soon as the interlayer opens up, the specimen fails, and there is no change in the stiffness. Another interesting result here is looking at the effective addition of fibers. So that the bottom two graphs shows a case with 0.3% fibers and with a case with a 1.2% fibers. You can see that adding only a 0.3% fibers has a significant effect on the post-peak response of the specimen. And it basically increases the ductility significantly if you compare the degree of shear slip in non-fiber case with the fiber case. In the shear slip in specimens with fiber is almost 10 times higher than specimens with no fibers. And also by adding the fibers, we have this residual strength that specimen has. It doesn't fail suddenly as we saw in non-fiber specimens. So addition of fiber has a significant effect on ductility. But the disadvantage here is that by adding the fiber, we are reducing the, on average, we are reducing the shear strength of both mold cast and 3D printed samples. And this is consistent with the results reported in the literature. The fibers that you're using are flexible, they're synthetic fibers, and they don't contribute much to increase the shear resistance. Comparing the failure modes again and the DIC measurement, one interesting aspect is that when you look at the mold cast specimen, you see that we typically observe two planes of shear failure in an angle. But if you look at the 3D printed sample, we typically observe only one plane of shear failure, which was more vertical, and that was close to the interface between the layers. So again, this explains why the shear strengths of 3D printed samples are relatively lower than the mold cast specimens. The failure was more localized in 3D printed samples, while in mold cast samples, we basically use the strengths of the concrete matrix more efficiently. Another interesting fact here is that if you look at the failure plane, in the mold cast specimen, we have a higher porosity compared to the 3D printed sample, which is again something that is mentioned in the literature. If you look at the orientation of the fibers at the shear failure plane, in the mold cast specimen, the fibers have a random distribution, and that actually helps to increase the shear strength because the fibers are intercepting the shear plane. In the 3D printed sample, the fibers are mostly in the direction of printing. Therefore, they don't penetrate between the two layers, and that reduces their effectiveness compared to the mold cast specimen. Now I want to touch base on some of the work that we have done at the structural level. So we have worked on both finite element modeling of 3D PC structural elements and also large-scale experimental. And we are currently working towards large-scale experimental testing of 3D PC wall specimens. So looking at the finite element modeling approach, so we are using the software called LS-SINA. We started with Abacus, but we decided to switch to LS-SINA, and one major reason was the ability of LS-SINA to capture the pinching behavior of concrete. So we basically constitutive material models work better in our opinion. LS-SINA provides a wide range of constitutive material models. We investigated all and realized that concrete damaged plastic model, CDP, works best. In terms of modeling the interface between the layers, we use a combination of cohesive elements and constraints. Cohesive elements will enable us to capture the tensile and shear response at the interlayer. And the constraints will ensure that the concrete elements will not penetrate into each other. So a combination of the two provided basically exactly what we intended for the layer behavior. So we use the experimental results in the literature to verify our model. I'm going to only present one of the verification studies that we have conducted. So this was conducted on a 3D printed wall tested under axial load. Here you see the test setup. So they had an actuator that applied a vertical load. The wall had a dimension of 710 by 720, so it was mostly. And then they have another one with different dimensions, so different aspect ratios. We modeled the wall using cohesive and solid elements, and here is a comparison of the results. So in terms of the load deflection, the analytical model was able to capture the peak load, initial stiffness, and the displacement at the peak load with reasonably good accuracy. And in terms of the comparison of the failure modes, again, you can see that in the experimental experiment, they basically observed some crushing failure on the left corner and some instability due to bond failure between the layers. And we see a similar damage pattern in the finite element model. So once we had confidence that the finite element model works well, we applied it to investigate the performance of a single-story 3D PC house in Canada. So we came up with very simple floor plan, a very small floor plan. So there's 6 meter by 6 meter. And we included different openings in the walls to investigate the effect of opening on the performance of 3D printed walls. And we basically conducted finite element analysis and realized that if you don't do any specific measurement or near the openings, the localized stress near the opening can result in a failure at the interlayer. Once we investigate the effect of openings, we assume that the building is located once in Victoria, which is in the west coast in Canada, and has a high seismic region. And then once we assume it is located in Ottawa, which has a relatively low seismic is a relatively low seismic region, we calculated the earthquake base shear force for both buildings using the National Building Code and compared the capacity, lateral capacity of the building against these demands. So the results here are preliminary. It's based on several assumptions, but that's basically an area that we're working to basically investigate the performance of 3D PC houses at the system level using finite element modeling. Now, moving on to our efforts on the experimental testing. So we are working with Printera to test and print and test 10 large-scale wall specimens. Here you can see the dimensions of a wall. They're 1.8 meter high and 2.2 meter long. And you can see the cross-sectional view and the elevation view of the wall. So the main test parameters here are the wall thickness, which varies from 200 to 300 millimeter, the layer width, which varies from 35 millimeter to 50 millimeter, number of columns. So we can see that we have reinforced columns at the boundary elements. So in some specimens, we only have 2 walls. In some specimens, we have, 2 columns. In some specimens, we have 3 columns. The other test parameter is the wall aspect ratio. We all know that in the aspect ratio of the wall has a significant effect on its performance, and also the axial load ratio, which we vary from 5% to 10%, which is typical for the axial load on load-bearing walls in low to mid-rise buildings. If you look at the
you have 3 minutes remaining. Huh?
Sorry?
You have 3 minutes remaining.
Sure, thank you. So if you look at the test setup, we have a horizontal actuator that applies the load. And we are intending to do some of the tests under cyclic loading, some of the tests under a monotonic loading. In order to control the axial load on the wall, we are using post-tension rods. and the wall itself is anchored to the strong floor. So here are basically all of our 10 wall sections. You can see that the section type changes. So in some of the walls, we have 3 layers of 3D printed printing. In some of them, we only have 2. So the outer layer and the incline layer. The number of RC columns also changes. So this is basically our strongest wall that is fully reinforced with a high reinforcement ratio, and we have 3 reinforced columns in them. And also the aspect ratio of the wall changes. So this wall is shorter. It has the same height as the other specimens, but a lower length. Now, in long term, if you have funding, so it all depends on the funding, but if you have funding, our intention is to do a system level experiment using our shake tables. So we have 4 shake tables at Carleton, each with 6 degrees of freedom, and they can work independently or they can be synchronized, work together. And what we are intending to do is to basically build a scaled house and put it on all 4 shake tables and see the performance of these structures under an actual earthquake load. So with this, I would like to end my presentation, and hopefully you enjoyed it, and I will be happy to answer if you have any questions.
Yeah, thank you, Vahid, for the presentation. So it's very interesting that we came to know that that the structural test is very important. So we have 2 questions in the chat box. The first question is that can you please elaborate on the testing method that I have used to find the shear strength of the 3D printed specimens? Additionally, I have come across literature where tip is not pointed, but the thickness is around 10 millimeter. However, in this case, the tip appears to be pointed. Is there any specific standard or the procedure followed for 3D printed specimens? It's a long question.
So it's actually a very good question, and we had the same challenge. You have specific standards for testing under compression, for testing under tension, and also bending tests. But for shear tests, at least we couldn't find a very well-recognized standard to use. So we basically did a double shear test, which is common in the literature, and you position the blade such that the shear plane is right at the interlayer between the 2 layers. And we had a good success with that type of test, considering that the specimen is very small and it's difficult to position the specimen such that the interlayer is exactly at the intended location. But surprisingly, in most of our specimens, the failure happened at the interlayer. Working with 3D printed concrete, we realized that the variability in the test results is an important factor. So it's always good to do more samples and in order to reduce the effect of variability.
Yeah, true. So one more question is there. So they talk about what is the reason for finding the mixers with low C/S ratio while the real wall application is moving towards higher ratio?
So actually, the C/S ratio, we are intending to reduce the C/S ratio to basically reduce the cement content. Having the cement actually helps the 3D printing process. It helps its buildability and workability. So there is a significant effort here in Canada here and around the world to reduce the cement content. And the 6 mix designs that are presented are the result of a large number of trial and errors, because the mix is very sensitive to the printing condition. So these are basically the mix designs that were suitable for our 3D printer, which is a relatively small scale. It might not be applicable for a larger scale structures.
Yeah, thank you. Yeah, I think, yeah. So last question. It's very interesting to see the presentation. Yeah, did you adopt any code any code for designing the wall?
So that's a very good question. So that was actually one of our challenges. There's no code to design these walls, and we worked with Marcus from Printera, who has very good experience on the field and the code aspect. So our designs are based on the masonry code. So we look at the provisions in the masonry code in Canada, and we make sure that we are satisfying the minimum requirements. And we also conducted an FE analysis to just make sure that the responses that we get from these walls are reasonable before actually moving on to the test phase.
Yeah, good. So yeah, I think that's all. No more question. Yeah, there is one question. In the northern Canada, we use elevated foundation. In this case, you should take into account some other structural elements that we need to test.
Yeah, so testing, it's just the beginning of the work that we are doing. There are lots of aspects that needs to be investigated: the connection of the wall to the foundation, the elevation of the foundation, and it's just our test will not answer every question. Our main intention is to look at the lateral behavior of these walls. I believe we are the first test that we are conducting in Canada. There has been a test at the University of Texas that I assume will be published soon on the lateral behavior of 3D PC walls, but I agree, there are lots of areas that needs to be explored.
Yeah, thank you, Wahid. So I think
you're welcome.
Yeah, I think we're running out of time, so I'll move to the next presentation, which is by me. Okay, so I'll quickly share my presentation, and we'll start. All right, so enter screen. So, yeah, I hope my screen is visible.
Yes, Branchi, we can see your screen.
Okay, thank you. Yeah, so hi everyone. So I'm Biranchi Panda, assistant professor in the Department of Mechanical Engineering at IIT Guwahati. So I'm from Mechanical Engineering Department, not from Civil, but I love to work in 3D concrete printing, material design. So a bit of structural engineering also. So today, as a part of this IC Impact sponsored project on 3D concrete printing, I'm happy to present some of our work that we have taken to design a sustainable concrete mix. So basically, we have been listening to other speakers that there's a need to print concrete because it has a lot of advantage. So we can print structures which are like very design freedom structures, and we do not need any kind of mold work to create the structures. The second reason we have that is sustainability. So we know that we can optimize the path, we can optimize the form to have a structure. In terms of sustainability also, we can get some more points. So basically, we have few reasons that we do not need mold to create structures. We can also optimize the designs, materials to make more sustainable design and structures. So basically, we know when we are talking about material development, it is very important for us to know how we should start doing the material development task. Basically, I keep on repeatedly telling the story that when we talk about the material development task, usually we talk about yield stress, and of course, the yield stress have to grow with time, because those who are working in other 3D printing techniques like plastic, metals, you might have seen when you print a we may print a material, it immediately get hardened. But typically in concrete printing, we still keep on printing the fresh concrete, and it keep on adding layer by layer. After some time, it got hardened. So when such scenario happens, so we expect that the material slowly going to get the strength, and if the material strength gain is very slow, then we get quick collapse. And in other way, if you see the material is rapidly hardening, then you may end up with a poor interlayer bond strength. So this is the game of 3D printing, where we have interlayer bond strength. So if you want to make a material having high viscosity, you may end up with a very poor interlayer bond strength. And if you make the material more flowable, maybe after printing a few layers, the entire structure is going to collapse. So there is a challenge here to design the material. Of course, there are so many papers, researchers, academia, industry has put their interest in this topic of designing new materials. So if I summarize the material development task, we can see in two different angles. The one perspective is that when you want to make printable materials, we start with printing a very low yield stress material, and we expect that after printing time of, let's say, 30 minutes to 60 minutes, the material is going to get its own yield strength. So that is the first approach. So what we do typically here, we start printing a very low yield stress material, and slowly it tried to gain its own strength, and accordingly to the printing height that we need, it is going to make up the strength requirement. But in some case, what happens, we may not use this kind of concrete material. We use some even further low viscosity material, but we try to inject an accelerator that keeps on improving the yield stress in a very quick time, and thereby also we can meet the target height. So this typically these two type of material formulations we have been seen in literature. If you want to inject accelerator, then you have to use an active extruder. So in the active extruder, you have a connection for injecting the accelerator. But in the previous case, if you want to start with a high stiff material, you can print it, but you need to have a very strong pump to push the material. So when these two type of material designs has been reported in the literature, what we have seen that we try to improve the sustainability of the mix by bringing a lot of industrial waste. So in the project that we are having from the DST and IC impacts, we try to make a more sustainable materials. So when we try to put more fly ash into the mix design, we have seen that after printing a few layers, the entire structure started collapsing. And when we investigate the cause of such failure, which is very well known, that we lack the enough green strength to have more number of layers. So to improve the green strength, yield strength, what we have done here, we try to use some kind of nano clay. As you can see, the very low dosage of nano clay enables us to have very high yield stress, which is helping us to print more number of layers without failure. So the nano clay is very important in this regard. We have seen that the nano clay that have been added into the mix design is helping to flocculate the material in the sense to have more yield stress. And this flocculation process actually helping the material to have enough yield stress to print more number of layers. But when we talk about in laboratory test to quantify the material for printing applications, in the laboratory, we recommend these two tests. If you have a rheometer, you can try to execute structural breakdown, or we call shear thinning test, or we have a viscosity recovery test. So typically what we do, we have a rheometer, we try to break down the material in the sense to understand how easily we can pump the material. So if you can see the graph that we have, I'm presenting here, there are two mix. So if I'm trying to break down the material, I can get an indication that which mix is easy to pump, or pumpability can be expressed through shear thinning process. And once we pump the material and print on the print board, the next factor which is very important, that is called viscosity recovery. So in the viscosity recovery, we try to see that once we deposit the material on the print board, how much viscosity the material can recover, so that we can add more number of layers without any structural failure. So these two tests has been commonly used in many papers, because if you go by slump test, slump alone is not a good indicator of printability, though in some paper they try to map the slump with printability window. But I feel thixotropy is a good material science, so where we can have a detailed investigation regarding flow of material, which is very important for 3D printing application. So this kind of clay we started using in geopolymer formulation, but we have found that in geopolymer, which is a purely alkali based material, we have a potassium silicate as an alkali activators. We have seen that if you add clay in the geopolymer, it has different influence on the material printability. So for an example, when we try to formulate the geopolymer mix, we have tried to vary the activated to binder ratio 0.35 and 0.4. We have two mix, one with clay, one without clay. So we have seen that the same nano clay that we have used in the case of Portland cement containing high volume fly ash, the same clay if we use to make geopolymer mix, the more clay we add into the mix, depending upon the potassium silicate level, we can get a variable yield stress and viscosity. But it is true that when you have high volume of potassium silicate, nanoclay role is not active. So nanoclay is not active because when you have too much potassium silicate due to high pH, they are not able to contribute their effect into the material design process. We have also seen that in India, there are a lot of applications where geopolymer are being used, and there are some Indian company who have approached to me that if you want to commercialize geopolymer 3D printing, because it is regarded as one of the sustainable material, how can we commercialize its dry form? So in the dry form, we want to say that it's 1 part geopolymer. In the 1 part geopolymer, we can add the dry potassium silicate, and we can simply add in water to easy commercialize the material. So here what you can see that we have tried to compare that in case you are using a dry potassium silicate and you have a liquid based potassium silicate, in terms of rheology how different they are. So we have seen that when we are using dry silicate, they are yielding high yield stress, which is very good for 3D printing. In fact, we have performed 2 material tests for Indian Army for the bunker applications. We have seen that when different materials is being used, dry potassium silicate is enabling better printability, but in terms of compressive strength, the dry silicate is not providing higher compressive strength. And when we investigate the reason behind that, we conducted FTR test, and from the FTR test we concluded that in case of dry silicate, we are having the absence of this SiOSi peak, which is indicating that if you are simply using dry silicate and adding water to make geopolymer, the potassium silicate activator is not completely dissolved and the activation is not proper. So therefore, we try to investigate how this kind of powder-based potassium silicate can be used in the geopolymer 3D printing formulation. And then we can think about different applications, and we have summarized different applications today. Professor Subramaniam also talked about that 3D printing can be used to create a more optimized structure. But if I summarize the application that has been reported till today, you will see that in concrete printing, there are one class of application where we print only the contour and fill with a secondary concrete material, which is a conventionally designed concrete. In other way, you will see that there are some applications where we print the concrete and use the structure as it is without filling the internal material. So on the left hand side, you can see we have printed one structure at IIT Guwahati. The material itself is 3D printed with internal architecture, and also Professor Subramaniam today discussed about the breeze that he has printed at IIT Hyderabad, which is directly 3D printed of the structure. But there are some application in the right hand side you can see where the contour has been 3D printed and then the concrete has been filled inside it. So typically we see these 2 kind of applications, and based on the application, the property that we test, the durability, the material property, all differs. So therefore, it is very important to first define the applications in which way you want to use the 3D printed concrete structure. You want to use it as a formwork or you want to use it as a structural element. This actually matters in different investigation. Since we talked about this lattice structure for direct application, so recently we published one article that by changing the design, the lattice wall design, we can also change the thermal property of these wall panels. So this article is just accepted for publication. So what we have investigated in this topic, that let's say you have a wall and you have a freedom to change the internal architectures. By changing the internal architecture and filling appropriately the insulation material, we are trying to optimize the design and material distribution to have better thermal property. And then, since this 3D printing is a process dependent material property, so it is very important to have a continuous tool path, because imagine that you are printing a large structures. If you are not providing a continuous tool path, then the discontinuity is going to create a problem for the structural applications. So we always prefer to print a structure with a continuous tool path so that the continuity will be maintained. So in that regard also, we have recently developed a TSP based print path solution. Using that, we can create a continuous tool path deposition where the material will start from one end and at the same point it's going to end the print path deposition. So there are a lot of examples we have tried to have a proof case of our algorithm, and like we have also done the similar case of study where we have optimized the breeze example, but instead of creating an architecture, internal architecture of the optimized part, we tried to fill it with a continuous tool path that is made by TSP programming. And then we have seen that when we are trying to deploy this kind of structural application, the challenges is the involvement of reinforcement. So there are stories that tells us that in concrete printing we cannot put more fibers, and also the addition of reinforcement is quite difficult because the machine cannot accommodate direct involvement of the reinforcement like we do in conventional construction. And of course, if you put too much of fiber, sometimes it's very difficult to add fibers for printability issue. And therefore, in our recent work, we try to take the help of fiber and coarse aggregate influence, because we have seen in some publication that if you have the coarse aggregate and also the fibers, because of the distribution and synergetical impact, we can create ductile concrete, which is very good for 3D printed wall applications, because this project is all about creating some kind of ductile wall that can take this seismic load. So we try to use the coarse aggregate and fiber simultaneously to make a ductile concrete. And as I mentioned it here, we have taken coarse aggregate up to 10 millimeter. Also, we have taken two fibers. These fibers are smooth fibers, smooth and straight. And we have the second category where we have taken corrugated fibers of different length. The smooth one is 15 millimeter length, the corrugated one, which is 30 mm length. So these are commercially available. And then we try to print using our custom developed extruder setup. So you can see in the extruder, we are trying to have more clearance in the screw area because we are passing the 10 millimeter aggregate during printing. And this is the mixed design table. You can see we have a reference mortar, so which is having 22 to 22 MPa strength in 28 days. And then we have added the 10 millimeter aggregate to make it concrete. 3D PC means 3D printed concrete. And then we have found out the critical fiber dosage for both straight fiber SF and this corrugated fiber CF. The this volume fraction has been found out for both kind of fiber, and accordingly it has been added to the mixed design process. So this is the typical flow from the Portland cement to sand, and then we have added the viscosity modifying agent. The SP was added into the water. After we make the mortar, then we have introduced the coarse aggregate up to 10 millimeter particle size, and then we made a concrete. And this concrete was further added with this straight steel fiber and corrugated steel fiber to make this kind of fiber reinforced concrete. And then we printed this material to examine its property. So in the mechanical testing case, we have only considered Z direction loading, because we imagine that if you want to print a wall, typically in the Z directions, we are going to apply the loading. And we have seen that how compressive strength, split tensile, and your 3-point bending test results are varying based on the mixed design. So we have 3D PM means complete mortar without aggregate. 3D PC means we have coarse aggregate, and the effect of this straight fiber and corrugated fibers are well defined in this presentation. So what we try to see, if you see it from the mechanics point of view, we have seen that by addition of this coarse aggregate and this steel fiber, we are enabling the crack bridging, and therefore we are improving the property for the seismic loading applications. And therefore we have taken two more parameter, that is ductility factor and reinforcing factor. So these two factors are determined to have a conclusion remarks that whether this material that we have developed by addition of coarse aggregate and fiber, whether they have any additional property or not. So, and if you have seen this material through microscopic view for the failure mechanisms, we have seen that the straight fiber is not sufficient enough to hold the crack. And in that regard, the corrugated fiber are performing well. So you can see from this kind of fiber bridging action, the corrugated fiber, they're arresting the crack. And also the presence of this coarse aggregate is also trying to deviate the crack propagation. So also this is confirmed through the micro-CT scan test. And ultimately, we have trying to put forward this material for the 3D printed wall application. And this wall are going to be tested under cyclic loading conditions. But one thing we have also found that when we are printing concrete, as Professor Bahid mentioned, the variation is also important. So to counter this variation, we investigated that if you print a long, tall structure, how the property varies from top to bottom. So therefore, what we have done, we have printed a tall wall, and top, middle, and bottom, from the three portions, we have taken three different samples, and we just conducted the tensile strength to understand, in case I am printing a single wall, whether the property from the top, bottom, and middle are uniform or not. So again, these conclusions are purely based on how you are printing. So normally what we have done during our gantry scale printing, we have seen that the bottom layers, as you can see in the crack propagation pattern, the bottom layer simply cracked without any deflection in the crack pattern. But when the material was getting printed, due to some defects in the top layer and middle layer, we have some clearance between the two consecutive layers. And this crack, whatever the defects that was initially present, this somehow help us to have crack deflection, so that we got a better property in the top part. But again, we are repeating this test to confirm whether this same thing happens repeatedly, because we have been seeing that if you are not printing 3D printed materials in a proper sequence, proper optimized condition, the property may have more variations. And to mitigate these variations, recently what we have done, we have tried to put a digital twin system with our concrete printing system, so that every time we print, we always take a record of what is being printed. It is very important for the quality aspect. And if you want to make some kind of design guidelines or some kind of robust quality checking control, so in that way, this kind of data are very helpful. And we have a plan that this data are going to be fed through a machine learning based network to tell us that where exactly we can optimize the mix, or maybe the process parameter, to avoid such kind of inconsistency in the filament deposition. So with this, like I conclude my presentation. So we look forward utilizing this mix for our 3D printed wall application. So if you want to know more about the process, the calculations that we have done, so I'm sharing the paper of my PhD scholar. Bustans, he has published this paper in Additive Manufacturing Journal. So you can check this paper for more detailed calculation. So with this, I conclude my presentations. If you have any questions, I'll be happy to answer it. Once again, thank you, everyone.
Thank you, Biranchi. So thank you for the great presentation. We have a couple of questions. I don't know if you are okay to go over the presentation, or I can read it for you. Let me know which one you prefer.
Yeah, I can read it, no issue. So is there any method to determine the yield strength of the material in its wet stage aside from traditional strength testing after hardening, because wet strength is crucial? Yes. So if you want to know about the wet strength, like in green strength method is well established. So you can perform green strength test to find the wet strength, because while you are printing, the green strength of the material is key aspect. So if you know the green strength of the material, you can also predict the number of layers you can put without failure. So there is a green test method you can see in the literature. So it has been used in many papers to know the wet strength of the material. If the strength of the specimen is measured when completely dry, how reliable is the result? Additionally, are there any methods available to measure wet strength? I think the same question. So wet strength, I think you can refer to green strength method. So we have also conducted the green strength, but again, it depends upon the stiffness of the material. If you are printing a very fluid material, the green strength test is not suggested. Typically in the lab, we print a bit stiff concrete. As I told you, for printing of stiff concrete, you have to pump it with a high pressure, but such a stiff material, you can use it for wet strength testing. But if you have a very fluid material, these tests are not suitable. Yeah, I think one more last question is there. So it's regarding that, as you are aware, preparing printable machine. Okay. So regarding design of expertise, DOE. So yeah, of course, there are some papers that have been following design of experiment guidelines to prepare the mixed design. So, but that is a more traditional approach. You can follow it. There is no problem in it, but it's also going to give you a systematic mixed design. But make sure when you are approaching to use design of experiment, you have right set of parameters, which is very important. Because if you go for some random selection of parameters, it may have a very bad influence on the response that you are counting for designing the mixed design. So make sure you have right input condition for the design of experiment. So in my work, we have not used any design of experiment, because we have already done a lot of trial test, and from the trial test we came to know this set of mixed design are going to work for our machine. So if there is no question, I think I'll move to our last presentation. Already we are running out of time. So our next speaker is Parivartan Reddy. He is the co-founder and CTO of Twesta, so a leading construction company in India. So he has dual degree from IIT Madras. So without speaking much about him, I think let's hear from his pioneer work. Anyway, I think most of us know Twesta. They have been the key startup, one of the important startup in concrete printing area, they have been doing a lot of great projects. So I welcome Dr. Parivartan. So please, the stage is yours. You can start your presentation.
Yeah, thank you, Professor Biranji Panda. Good morning, everyone, and good evening. I think in India it's already pretty late, so I'll try to keep it like really quick, and I'll try to keep the presentation more visual. So I'll just share my screen right now.
Yeah.
I hope you can see my screen.
Yes, it is visible. Yeah, please make it full screen.
Yep.
Yeah, thank you.
Yeah, so what I'll try to do is I'll try to give a bit of understanding on how these projects come to life and what goes behind the projects. I mean, primarily from the printing point of view, to just give an understanding on how the machines print and what are the different types of machines that we use. Yeah, I mean, we started our company in 2016 to just give a brief about Twasta, and then we started working on construction 3D printing. I'll quickly start with a video which sort of broadly covers the 3D printing process. As you can see, like material is deposited this is how a typical walls look. It will be like some bit of the walls we follow, and if you want to integrate any steel during printing, we can do. And post insertions we can pockets and so this is broadly like this is the things that that will be there in the 3D printing thing. We have 3D printer, we have materials, and we have. These are the different kinds of printers. This is some printer. Again, we'll just different kinds of printers, but this is a on-site printer. This is a mobile printer which has like so this is a typical process. I mean, we start and then there is a software where we load our is then converted to a code, and this is the architecture software we use to generate like different patterns. So and then this is the printing goes. File gets fed to the printer, and then these are some of the buildings that we have. Showing yeah, that's a quick video on. Okay, there seems to be some problem with the slideshow, so I'll try again a little later. So these are the broader level of things that in the 3D printing, broader we can call like broader departments or broader segments. One is the machine, one is the material, and then there's software, and also like the print strategy. So if there is a model, how it has to be printed, what is the tool path for it. So so these are the broad level of categorization. So I'll just quickly show you a couple of projects, then get into the machines, and then again come back to the details of the project execution. So this is a recently completed villa project that we have done for Godrej. It's a G+1 structure done on site. So basically, we have taken a large gantry printer, assembled at the site, and then did this in one go. Just to give a glimpse of the finished. We have designed the building so that
Pariwanta, sorry, I'm interrupting you. I think when you're talking while the video is playing, your voice is cutting out. So when you play the video, I think there's something wrong with your voice.
Sure, noted. So I'll probably turn off the audio in the video that I'm running, and I'll speak over it. So hope the audio is clear now. I mean, my audio. So yeah, this is just a glimpse of the project. As you can see, we have taken advantage of 3D printing capability, and we have added some curves and some sort of facade walls into the building. So this is the final output. So this is a 2,200 square feet building. Each floor is 1,100 square feet. Yeah, these are some of the other views of the building. If you see from the top, it is actually inspired from multiple geometries putting together and then forming a pattern. Just to so in broadly, like in 3D printing, we have two strategies. One is offsite construction, one is onsite construction. So the previous building that I have shown is something on-site construction. We have taken the machine to the site and did the construction. Whereas offset construction is where, like in factory, we build the blocks, take to the site, and then assemble them. So this is a prototype small building that we have done. So where I'll just show you how this small modules on the structure. So it starts with a design process, and in the design process itself, we sort of break the modules. We split the modules into the desired geometries. And you can see different modules can be of different shape, different size. And we sort of label these modules and then plan the production queue. So this is a typical way of offset production. And then we go about printing modules one by one. In the end, we will have all this stack of modules which are labeled based on the location they go. We can integrate some of the some small steel elements inside. And one interesting thing is we can also make this as interlocking blocks. I mean, not perfect interlocking, but still that gives some sort of reference during assembly, and which will sort of arrest the motion and give references. And then after printing of the modules, it goes through a quality check phase, and then we take it to the site to assemble. Yeah. So this is the typical offset construction. And these blocks can vary. I mean, in this case, the project was designed in a way that these blocks are hand carryable, but of course the blocks can be much bigger, and then we can use cranes to assemble. Yeah. And so again, as I was telling, there are many applications. I think in the previous presentations also, you have seen different sort of applications with 3D printing. So 3D printing is a versatile technology. We can use it from small flower pot to bridges to bunkers and large scale buildings. So I think there are a lot of different possibilities that are there with 3D printing. So what I am just showing are few applications, but of course there are many more applications that exist. So these are something called as coral reefs, where these are deployed inside the sea coast for the growth of coral. So this one here we are using a robotic arm, and file is fed, and then the printing process goes on. Okay, there seems to be some problem in the video, but it's similar, like, we feed the model and then the printing goes on, and then we sort of deploy these things. Yeah. Again, I mean, I think a lot of benefits with 3D printing, and I think they're already covered in the previous presentations also. So we can save material by, like, as you can see in the videos that are going down, there are like a lot of hollow pockets, so we can save material in the walls, and we can design these walls so that they are, like, more thermally insulated in nature, and we can add certain textures to the walls. So there is a lot of design freedom in how we design a wall. So to some extent, we can integrate MEP, we can plan where the switch boxes are going to come. We can integrate that during the printing. So a lot of flexibility is there during printing stage, and we can actually make it like an integrated wall instead of just looking at it as a just a wall. It has like features of integrating like columns inside it, integrating MEP inside it. So it's like a more of an integrated wall. These are some of the projects and different types of projects that I'm showing here. So on the left-hand side, this is called like a pod units. So where like larger modules are printed, and then they come to the site, and then we assemble them together. So as you can see, like, if it is in a precast, for example, the module will be like same across. Whereas with 3D printing, each module can be different, and then we can form these unique shapes. On the right hand side, this is a bus shelter. Again, we can see different sort of modules coming together and then forming this larger level shape. Yeah, this is a boundary wall that we have done for cricket stadium. So again, here, like, different panels, you can see like has different textures. So whereas in 3D printing, typically we see these horizontal grooves, but we can also add this texture along with the horizontal grooves. There can be projections, and then it can form like this larger level patterns. So this is can you see this video? It has switched the window, so not sure if you're able to see this window.
Yeah, we can see. So as you can see, like, this is a 3-meter tall wall, and it has 400 meter, and there are like different patterns going across. So we have stacked it in 2 levels, like each panel is 1.5 meter, and then we have put 2 panels, 1.5, 1.5, and then there are like, columns running in each panel. And just coming to like printers, like how do we actually print this, and what are the different kinds of printers like, right? So we have printers ranging from gantries to robotic arms, and even polar coordinate printers. There are even boom type printers. So there are multiple types of printers in the market. So just giving like few types of printers over here. So ranging from like very small scale printer that are typically used in like R&D labs for material research, or like for structural research or different types of researchers, and slightly larger scale production printer, like where we can use it for like producing panels continuously, and or like even a bigger gantry, so that goes to the site and then builds like something like villas. So and similarly in robotic arms also, we have either stationary robotic arm, or like robotic arm can be mounted on like a moving base, or like it can be mounted on a track. So depending on the application and outcome that is expected, so different kinds of printers can be deployed. So this is an example of a small R&D printer, where it's in the range of like 1 meter by 1 meter printable area. And this is an example of a production printer, where you can see like some panels are getting printed continuously, one after one.
And this is a large scale on-site printer where you can see some people sitting over here for reference. So it's a large one, and it's basically broken down into multiple modules. We take them to the site and then assemble them at the site. And these are robotic arm printers. As you can see, the footprint of the printer is very small, and we can keep printing objects like this. This is a mobile version of the printer. This is a rail-based robotic arm printer. And this is a polar-based coordinate printer. You might have seen larger tower cranes at buildings. So similarly, there is this is a kind of a printer which works on a polar coordinate system. And then before going for the actual print, we can always do simulations in the softwares. So whatever we want to print, we can test it fast, whether there is any sort of issue with the printability path, or is the path how we have visualized. So all that can be done. And this is an example of a non-planar print. So with using robotic arms, it need not be so mostly we see layers getting stacked in a Z direction, right? So using robotic arm, it has 6-axis degree of freedom. So the layers can be slightly inclined also to some degree till the material with holes. After certain threshold of overhang, the material will collapse. But till some overhang, we can use this robotic arm capability to do that non-planar layers as well. And these are some of the projects just to give an idea on different kinds of structures that are possible. Even from simple structures like small modules to houses, different kinds of structures are possible. And we can integrate some walls to be flat, some walls to have textured output. So for example, some facade wall like this, the modules get printed in the factory, and then we take them to the site, and then we assemble to form this sort of structures. This especially is designed for sort of having giving a wind flow direction to it. So when the wind hits the wall, there's a path to escape. So something like that, it need not even be only for a facade or only for aesthetic appeal, but we can bring in the functionality to the facade as well. So we can leverage 3D printing to do those kind of things. Again, just how this bus shelter comes to life, right? So how do we print it, and then how do we assemble it? So this is what happens in the background. So it a production sort of a printer prints these modules one after one, and then these modules we bring it to the site and then assemble them. So that's the background process. So you can see something like a complicated concrete structure is done. So which otherwise would be extremely difficult to do with any other conventional method in concrete, right? So how do we actually do this? How can we make this happen? I'll just show you a quick video. This is a pretty long video, so I'll be just skipping some aspects of it. So it starts with architect thinking about some sort of a concept in their mind, right? And then we go through different design iterations, and then that is initially conceptualized, and then it goes through a stage of structural simulation. So how the reinforcement should go, and where are the stresses coming, so what is the strategy. So it goes through that process, and then comes a printing process where we print the modules. So this is we have printed in segments, multiple segments, and then taken them and assembled them. So this is the assembly process where you can see some steel running through these columns. So here, basically, we have used this as a formwork. And then modules get assembled, and this is the final outcome of it. So yeah. So which otherwise, without 3D printing or with using any other technology, building such concrete structures would become extremely difficult. So that design freedom, is a very strong advantage of 3D printing. Again, just to run through how again this process happens. I'll show you a video of printing and then how the modules get transported and then how they are assembled at the site. So this is a small site office we have done.
Maybe you can complete in 3-4 minutes, huh?
Yeah, sure. Okay. So again, this is how the design initially gets done, and then we print the modules. As you can see, this module has like certain diamond sort of a pattern that is coming on one side, other side it's flat. So these are modules get printed, and we transport them to the site. Here, like we have done a conventional foundation, and then we assemble the modules. So again, this is another example for a offset construction. Again, this is a boundary wall. You can see again the patterns and textures that are possible. Similarly, like a lot of security cabins is another application that can be done. So here we have done roof also as 3D printed. So basically, roof is also another printed module that we have taken and assembled on top. These are like where in this project we have taken the robotic arm to the site. It is assembled and then it is doing the construction process here. So that's how the structure is achieved. So this is the pods that I have shown before. So different pods, this sort of modules are printed, taken to the site and assembled. And this is another project we are doing in collaboration with IIT Madras and Professor Manu Santanam sir. So where, as you can see, the complicated nature of this project and the structure, right? So it's a quite challenging structurally also, and also from execution point of view. But I think because of 3D printing, it becomes like little simpler compared to any other way to sort of make the structure possible. So yeah, these modules get printed, and we take these modules and assemble at the site. So, and another applications we have are like such landscape elements, facade elements, and indoor indoor tables, outdoor tables, and such cases. Such applications are always there. Yeah. Thank you.
Yeah, thank you, Mr. Parivartan. It's great to see all your projects in India. So since you are into large-scale deployment of 3D structures, I think the audience, they wanted to discuss with you regarding some costing. I can see that from the chat box.
Okay.
So I'll take the first question. So could you please elaborate the influence of interconnected reinforcement observed in the blocks? Have you quantified their impact on the mechanical property of the block?
Yeah. So similar to what we call this as, wherever the reinforcement is coming, we can imagine this as a sacrificial formwork or formwork left in place, right? So typically, like we have this wooden shuttering coming, and then there is steel running, and then we put the concrete and then remove the wooden shuttering, right? So in these areas, like where there is like steel coming, so this stays in place, but this also acts as a formwork. But otherwise, there are a lot of studies happening on load-bearing walls and how do we sort of minimize the reinforcement that is being used. So there are different sort of processes, but where we are integrate steel as a column, this acts as a formwork.
Correct. So there is a question on the cost. So what is the cost variation of 3D printed structures compared to traditional methods? As Professor Shrikant mentioned that it cost around 5 to 6 lakhs Indian rupees.
No, I think I would like to correct that. I think that's not a right figure, and I think that project I'll discuss with Srikant Das sir, and probably will correct the numbers there. But yeah, see, typically it all depends on the design. It depends on the the number of projects. I mean, the quantity of volume that needs to be done. So, for example, if only one building needs to be done, and the printer has to be mobilized, and team has to be mobilized for that. So typically, all that costs get added into the single building. So in that, the project value will go up. But in case there are like multiple projects in the same location, and once we send the printer gets occupied and continuously operations are happening there. So then the cost comes down. So it's all about scale and the type of project.
Right. Yeah, one more comment is that excellent work, good. So you have several projects. However, it is please provide some insight regarding the design aspect, reinforcement detailing for the wall panel and slabs. We audience will be happy to hear this.
Yeah. So yeah, in see slabs wise, the currently there is a limitation with 3D printing still. I mean, of course, like when used as a roof, I mean, we can print the panel and then sort of lift it and then put it in one of the security cabin. I'm sure we have used that way. But still, like printing horizontal members is a challenge because for 3D printing, we need some support to print on top of it, right? So I think there are different kinds of studies that are happening on how to sort of do this slab work or horizontal element work, but still that's a challenge. So what we do with the slabs is we either use like precast slabs or conventional slabs, and we do that. Sorry, there was one more part of the question, right? Is that?
Yeah, they wanted to know regarding the reinforcement detail about the wall panels and slab.
Yeah. So reinforcement wise, like typically there are different strategies we can take. One is either we can consider as a shear wall, like where we can have like similar to shear wall, like steel running all over, like single rebars running all over, and then we print around the rebars and then have like some horizontal ties to it. And or like we can always we can follow like a column beam approach, like where there are like in certain locations there are like columns coming, and certain after certain height like there is a beam coming. So it's similar to like either we follow, because like the codes are still evolving. So the codes right now are referred to are like conventional codes, like either a RCC, either a RCC column beam sort of approach, or it's a shear wall approach. But I think as in the next few years, like we'll be seeing probably more optimized strategies for 3D printing.
Right. Yeah, thank you. So I think we do not have any questions in YouTube also. Yeah. So once again, Mr. Parivartan, thank you very much for spending the time and detailing all your projects to the audience. I think they have learned a lot of things. So with this, we come to an end of our symposium. So I request all the co-hosts and all participants to please switch on the camera for a group photo. I know it's too late in India, but still we would like to capture this moment. So if you don't have an issue, please switch on your camera. So
please don't be shy and turn on your cameras. We want to take a good photo. And if you can just stop sharing the screen so we can see all the.
Yeah, we can capture it. Close it.
So I slowly see more faces.
Yeah.
Wait for another minute.
Yeah, dear everyone, please switch on your camera. So we just want to capture the photo. Yeah, we see more faces now.
So Biranchi, do you want to take the screenshot?
Can you please do it? I don't have mouse, so in MacBook I think I don't have.
Okay, sure, I will do it. So 1, 2, 3. Let's do one more. Sorry. So one more. 1, 2, 3. Okay, thank you everyone for joining the session, and hopefully this will help us to collaborate more in the future.
Thanks everyone.
Yeah, have a good night in India and good afternoon in Canada.
Thank you.
Bye.
Thank you, Vahin and Belchi, for taking this forward, and thank you to all the audience for joining us. Indeed, a pleasure to interact with all of you. Thank you.
Yeah, thank you, sir. Thank you, everyone.
Thank you.
Thank you, everyone.